Good morning, everyone. Welcome to the last day of this year's Quantum Summer School. Welcome. So my name is Yuhan Chen. I'm a PhD student from Purdue ECE and will serve as an announcer for today's talks. So let's welcome our first speaker, Professor Chris Brinton. Professor Brinton is the Elmore Rising Star Assistant Professor of Electrical and Computer Engineering at Purdue University. And I know that recently Professor Brinton has been promoted to Associate Professor starting this fall semester. His research interest is at the intersection of the networking, communication, and machine learning, specifically in the fog edge network intelligence, distributed machine learning, and AI/ML-inspired wireless network optimization. Dr. Brinton is a recipient of the National Science Foundation Career Award, Office of Naval Research Young Investigator Program Award, Defense Advanced Research Project Agency Young Faculty Award, Air Force Office of Scientific Research YIP Award, Intel Rising Star Faculty Award, and roughly $16 million in sponsored research projects as a PI or co-PI. He has also been awarded a Purdue College of Engineering Faculty Excellence Awards in early career research, early career teaching, and online learning. He currently serves as an associate editor for IEEE ACM Transactions on Networking, and previously was an associate editor for IEEE Transaction on Wireless Communication. Let's welcome Professor Brinton.
Thank you. Thank you so much, Yusheng, for the introduction. Thank you all for being here, and thank you for inviting me. It's always great to come here and be able to share some research that I've been working on. The intersection between machine learning and communication systems, the communications domain. I hope that what I'm talking about here can give you a lot of insights, into how you can apply some of these techniques, particularly in the design of, quantum computing, quantum communications. I think it's a very exciting area, certainly to investigate. And so, as said in the introduction, my research really is at the intersection between machine learning and communications, particularly in the wireless communication domain. And so I'm going to tell you a little bit about the motivation behind some of what I do in some particular threads of it. So today we have, billions of connected or IoT, Internet of Things devices, right? So just think of, your smartphone. I mean, each of you probably has 2 or 3 devices, maybe not connected to the internet right now, but I'm sure you all at least have one device that's currently on Wi-Fi or whatever it may be. And, as a result of this, both user-generated and machine-generated data, there's, explosion, literally an exponential generation of data. If you plot it on a curve, it's actually an exponential growth function from, say, the Internet of Things. And that's fueling lots of great advances in AI and machine learning, right? I mean, all the buzz today has been around large language models, right? So everybody knows ChatGPT. I'm sure maybe you've used it in some of your homework assignments. Hopefully you don't rely on it entirely when you're doing your homework, but people have definitely been using that. And that's so a lot of this comes from all of the language data that's available from billions and billions of users over time, right? And we also, at the same time, we have advanced edge capabilities, right? So, which actually drives the growth of that data. So, providing these advanced edge capabilities is a principal objective of 5G, 5th generation wireless. 6G is the next. That's what we're looking at now. 6G wireless, 6G and beyond, right? So, the ability to have really intelligent services that react based on your local environment and preferences on your phone in real time, right? These are all really key objectives of these wireless systems. All the generations, in my view, seem to always fall short of what the initial expectations were, but a lot of that probably has to do with the mismatch between marketing and what's actually being done in engineering. But certainly now we have a lot of machine learning services that are even in your phone, right? Driving wearable health analytics, augmented reality, virtual reality. Some of you may have do that in your spare time or even in different classes or laboratory settings. A lot of these are data intensive applications, right? And they're also latency sensitive, okay? Which are 2 things that are kind of fundamentally at odds with one another, right? The more data you have to process, you would think is going to take a longer time to do that, which it does. So if you need things quicker and faster latency, but you have to process some more data, that's 2 really hard objectives to keep optimizing over, right? So we need to come up with good solutions for ultra low latency and high reliability communication. So Then it motivates AI and ML driven protocols. So the internet was designed, we had earlier this year actually the fathers of the internet, or some, I would consider them to be fathers of the internet. Vint Cerf and Bob Kahn were actually here on campus. So they came up with the initial protocols that are driving the internet and how internet traffic gets routed and how congestion control works. Back in the late 60s and the early 70s, right? Since that time, really, the internet protocol stack hasn't evolved all that much in terms of how it's modularized. Certainly, the protocols have become more advanced, but with AI and ML, it gives us an opportunity to even rethink the way that the internet even is architected. So we can start to look at cross-layer optimization based upon machine learning. So all the way from the physical layer and way that bits are put across in the internet, how they're actually modulated and put onto a data stream in terms of bits and ones and zeros or qubits, right? All the way up to the application layer and the applications that are generating those measurements in the first place. AI and ML gives us ways of potentially learning new protocols for governing that cross-layer. And there's also some new network paradigms that have emerged. ORAN is Open Radio Access Network, so the internet's becoming more and more open for users to be able to do experiments on, for users to be able to innovate and try to come up with new, fundamentally better protocols. But at the same time, a caveat to that, it also makes it much easier for people to attack you, right? Take your data, run some de-anonymization attacks, try to thwart whatever you're doing, try to throttle your traffic, right? So security in an open system becomes much more important for us to be able to manage. So this is kind of the area that I work in, and trying to look at how do we tackle all these objectives, right? Keeping the internet open, but also keeping it secure, trying to maximize the ability to have data, right, and intelligent analytics at your fingertips without, say, causing an explosion in the amount of energy your device has to be consuming in order to process all of the data and so on. And this process occurs all the way down from the end devices all the way back up through the main servers and the cloud servers. And even today, we have satellites, right? The Department of Defense is very interested in satellite communications today as well, and how that can help with certain access to internet and connectivity in areas that don't traditionally have that kind of great access, right? And so this whole continuum of resources from the end devices all the way up to the main servers, and trying to actually optimize and orchestrate intelligence over that. That has a lot of really interesting research questions we're looking at. And so in my work, what I look at is trying to come up with new and really scalable ways of training and managing machine learning algorithms over large-scale network systems, okay? Back around 7 or 8 years ago, Google came up. Of course, it's always Google, right? Or Amazon or Facebook, I guess, or Meta, I should say now. But Google came up with this really cool algorithm called federated learning. Some researchers there did. And federated learning has a lot of really nice advantages in terms of solving some of the challenges that I had just laid out, okay? In particular, what federated learning says is, since users may be concerned about sharing their data, let's not ever have them share their data, okay? Because traditionally, what machine learning training requires is it needed the data in a central place. So if I wanted to train, say, an image classifier across all of your phones or all of your devices, I would need your data, right? I need all the images that you've taken. I need my images, I need your images, I need Sasha's images, I need everybody's images. So across all the data sets that I want, in order so that I can learn a classifier that when I get a new image, I can classify it as, an animal or a human or cat or dog, whatever, right? But people don't like to share their data. So Google said in federated learning, forget that. We're not going to have you send your data at all. Let's have you train the model yourself on your own data, okay? Train it on your local data and just send me the model that you train. And I'm going to take the model from everybody. I'm going to take everybody's model. So I don't need access to your data. I just need your model parameters, the little weights on your neural network. And I'm going to take them and I'm going to average them and I'm going to send it all back to you and synchronize all the models and then have you keep training on your local data. Again, send it back to me, I'll average them. And we'll keep doing this back and forth, this iterative process, okay? So I'm bringing the model to the data rather than the data to the model. And that's great because it's very privacy preserving, right? You don't have to send your data, you're just sending the model, right? So you wouldn't think that I could reverse engineer the data. Well, the problem is people show that you can actually do that. You can figure out what somebody's data was if you just send their model. In certain cases, if you have enough information and make some assumptions, right? So it's not a perfect solution, but it's certainly a better solution. The other problem is that models now are huge, okay? You know how many parameters ChatGPT has? I mean, we're talking billions and billions of parameters. It tends to be larger than data sets themselves, right? Definitely larger than the amount of data that you're storing on your own local device. So the idea of you being able to actually train that whole model on your data on your smartphone isn't going to happen. You can't store ChatGPT in your phone, at least not yet, right? So this process has a lot of scalability issues. Also, when you just consider the sheer amount of devices that we have to synchronize over. I mean, we're not talking about just everybody's smartphones in this room, sending them to an access point. If we really wanted to train the best possible image classifier, I would need data from all over the world, right? So how am I going to get people to send all their data up to one single central location, right, in an amount of time that I need to be able to learn an intelligence model? Especially if that intelligence model is not just for fun, but it's like, say, protecting some national security threat. So if there's some new threat that emerges, or China launches something that we need to know about, I mean, that's our biggest adversary today, probably, right? We need to do that really quickly, right? Like seconds, milliseconds worth of latency. And so we can't wait for all the data to get sent up to a server, right? We can't even wait for the models to get sent up to a server. So we have to figure out, how do we fully distribute or intelligently distribute this whole process so we don't even necessarily have anything being centralized anymore? Can we fully distribute intelligence, in other words, right? A fully distributed intelligence solution is also one that has a lot of security advantages because there's no one single central location you can attack that will completely take down, right, the intelligence system, right? So there's three key challenges and opportunities that federated learning presents, in other words. One, I actually didn't really touch on this one, but is heterogeneity in local resources and data set statistics, right? So all of your local data sets are going to be very different from one another. So when you train your own model, you're going to be drifting away from what I train when I train my own model. We're kind of going in two different directions, possibly, or maybe not completely different directions, but some direction that's not 0 degrees. It's maybe 30 or 35 or 40 degrees apart, these two vectors, right? So that costs a lot in terms of needing to synchronize the models frequently to make sure that we don't drift away too often from one another. And also our resources are very different. I mean, maybe I have the newest iPhone. Maybe someone else is still on iPhone 7 or 8, right? Very different processing capabilities between those two phones, right? So I can run processes much quicker. I could train a model faster using less energy resources than a phone from, say, 5, 6, 7, 8 years ago, right? And a lot of IoT devices actually aren't necessarily just new equipment. They might be old equipment that suddenly was, added internet connectivity, right? So they don't necessarily always have the most up-to-date processing. So you have to deal with heterogeneous resources across the system when you're doing training too. Second is the topology, okay? Federated learning assumes that you have this really nice star topology from the devices to the end servers. But in practice, this is almost never the case. Usually you have some main server located somewhere, and you have, like, say, maybe these local clusters of devices, or even in a more extreme case, you have an entire hierarchy separating these end devices from the main server, right? So it's almost never a star topology, and assuming it's a star topology is really inefficient because you're not accounting for all the communication that has to happen. And all the scale, or all the communication burden that you're putting on this one single main server. And finally, it doesn't even account for proximity between wireless devices, which even within these local subnetworks, if I wanted to, say, connect two devices to one another, that's a key feature of 5G, 6G, and beyond, is that actually devices can do direct connectivity, right? I can airdrop something to you, right, directly. We can form peer-to-peer connections locally if we have good trust models for one another. That's really efficient too, because if we can synchronize our models locally, it reduces the burden upstream to the main server, right? But we also have to account for wireless factors, because if my device is right next to yours, it's going to cost a lot less in energy than if I'm sending something to a device that's, say, a mile away or something like that, or a base station. Okay? So we have to consider the proximity too. So we came up with this term called fog learning. Okay, so it's not federated learning, it's fog learning. The reason we call it fog learning is that fog computing emerged about maybe 10 years ago now, a little bit later than federated learning did. Fog computing is the idea of trying to orchestrate computing tasks across what we call this cloud to things continuum really intelligently. So it's not edge computing. Edge computing happens at the edge, near the end devices, right? And cloud computing is what AWS does and what cloud servers do. It's the fog in between the edge and the cloud, right? Fog is the intermediate. It's a cool analogy, right? I didn't come up with that word, but so we call this fog learning because it's trying to really innovate federated learning in a sense, but over these fog computing systems. So fog computing involves distributed orchestration to jointly optimize intelligence quality and resource efficiency. And it also involves actually employing state-of-the-art AI and ML algorithms to optimize and even defend networks. So it's a bi-directional relationship between fog computing and AI and ML. And so I work on really both directions of this, okay, where I build new AI and ML algorithms to innovate fog computing. And I also leverage innovations in fog computing to try to help improve the scalability of AI and ML. Okay, I'm going to talk to you a bit today about what we're doing in this first arrow here, from fog to AI and ML. Okay. So the research process that we tend to use, really, in any of the papers that, if you look at, that my group is publishing, is it starts from the theory, actually. So we theoretically try to codify fundamental relationships between a couple of different things. How the fog computing configurations, the specific topology of a fog network and the processes that we're running on that network, how that is related to the AI and ML training performance. Okay, so understanding, say, in a given computing configuration, how would sending information from device A to device B impact the machine learning performance? And also, in turn, the wireless resource utilization. How much energy does that cost to do that? All right, so understanding these trade-offs under the heterogeneity properties that are inherent in these systems. These are really complex relationships, and we try to find them, and not just for the purpose of finding them, but so that we can use them to come up with really nice orchestration algorithms to jointly optimize between objectives that may be competing, right? So we have, some set of competing objectives. We want to optimize the intelligence quality, minimize the loss, want to minimize the resource consumption, energy, and whatever else it may be. We may want to minimize the latency that's required in these systems, and so on. So we have a whole set of competing objectives that we need to optimize between. And so we go from the theory to developing these algorithms, and then, of course, to the experimentation, right? And they refine each other, right? So because there's certain things that we need when we develop an orchestration algorithm, but we need an objective that we can develop a nice algorithm to optimize for. So if it doesn't have certain properties, right? Like one property that's really nice in machine learning, which we almost never have, but is convexity. If a loss function is convex, it means it has a single global minimum that we can find. So we know that when our gradient descent process ends, we're at the optimal point. That's almost never the case, but if we can come up with approximations that maybe are convex or quasi-convex, something like that, that really helps us to build much more scalable algorithms, okay? Because when we build an orchestration algorithm too, that itself also requires resources to actually run, the orchestration algorithm. It's resource intensive, right? So if I'm in a sense adding more complexity in order to try to reduce complexity in the first stage. So I have to make sure that what I'm adding is worth it, right? And so on. So there's a lot of considerations here that we need to make, but they reinforce one another. So if I need something better from my convergence analysis, I can learn that from the orchestration stage and learn, hey, well, I need to try to find a relationship that's a bit more tractable from an optimization standpoint, and so on. And then maybe we throw it on a test bed and find that none of it works at all. And so we have to just rethink the theory that we're developing, right? So it's a nice kind of feedback process. Okay. So when we build fog learning, there's a couple of design principles that we try to incorporate into the system. Okay. We start with four main principles here as we're looking at this whole hierarchical process. One key design principle that we try to include in here, I've mentioned before, is this idea of device-to-device, direct device-to-device communications. So not all model or data sharing has to go upstream and downstream from device to server, device to aggregator. If we can just horizontally share information at certain times, it might be much more resource efficient and much quicker to do that, okay? So we want to include that within the system and understand what it means and when it's better to do than going upstream and downstream. We also we need to be able to adapt the frequency at which we do synchronization across this hierarchical system, okay? I may need to make sure that my devices at the edge, right within a given cluster, are synchronized much more frequently than, say, devices that are very spread far apart across large geography, right? They may not need to synchronize as often, but if these are, say, a set of robots that are trying to coordinate some task or do something, right, in real time, they need to synchronize much more frequently than they would, say, across different clusters, right? So we can get some energy efficiency advantages by tapering the frequency at which we actually do the synchronization, the aggregation. We also want to integrate protocols for resource allocation and machine learning training into this directly, right? So the machine learning can optimize the way that we're orchestrating the system and vice versa. The way we orchestrate the system can optimize the machine learning. And finally, perhaps most importantly, whereas in federated learning, we're only distributing the ML update process, but the aggregation process remains centralized. In fog learning, we want to distribute both of them. Both the update process and the aggregation process should get distributed throughout the system. So as we start to look at fog learning, one of the key ideas that I mentioned is this idea of having decentralized fog topologies, right? So we have a whole large set of different topologies that we have to be able to look at and understand how this process works. And so a lot of the work in my group, which, well, I only have a couple of, maybe 10 minutes now, but I would like to give you an overview of some of what we've done in studying two canonical architectures for fog learning, okay? And they're really related to different levels of decentralization. So in a semi-decentralized fog learning system, we have some kind of a coordinator hierarchy that's available, right? Like say from our devices to a base station and so on. But we're going to assume that communication through it is costly and that it should be used as sparingly as possible, okay? So we can still do some device to server communication, but we want to minimize the frequency at which we do it by introducing intelligent local communication, right? And so we've had a lot of work that we've done here, actually ranging back to 2021, basically, on semi-decentralized fog learning. And then in a more extreme case, there's certain instances where we don't have a coordinator at all, right? Like in a distributed orchestration setting or some even consider a defensive setting, right? Where you don't want to be sending data even back to a command center with fear that it might be taken by an adversary in some way, right? So if you want to completely get away from any centralization, this is the fully decentralized case, which we've been working on a bit more recently, okay? So importantly here, we have to consider intelligent ad hoc wireless link formation. The formation of links, and when forming links between devices is important for optimizing the intelligence process that we're running over the system. How does the formation of links between nodes impact the training process, and what should be the nature of the communication over such links? Should we be sending data? Should we be sending models? Should we be sending compressed models? Should we be sending just a fraction of layers within a neural network? You can do that too. Okay, so we've had a bunch of work in this area, and I just highlighted a couple of here that I was going to just briefly talk about. So what do we mean in this semi-decentralized system model? Get a little bit mathematical here. So there's three processes to formalize. At the end devices within the end clusters, right? So these edge devices, IoT devices or smartphones, we have local model updates at the devices. These are gradient descent iterations that are executed on the local data sets, okay? So that's one process. That occurs at one time scale. It's the fastest time scale that we have. Then we have another time scale where we have local model aggregations amongst ad hoc clusters of devices. So within these local clusters, we'll do aggregations, but locally. Normally when we think of an aggregation, it's a global aggregation and fully synchronizing the system. These are like partial synchronizations that occur just within these individual clusters. But they're facilitated not through vertical communications, they're facilitated horizontally, okay, over the D2D topology that we formed, okay? So importantly, they don't occur in a single instance, right? I can't just get all the models at once and aggregate them because I don't have a centralized way of doing that. Instead, I'm doing them over some type of an adjacency matrix. And so that process too of aggregating the models within these local clusters is itself also an iterative process. And that gets into actually control theory when we look at decentralized consensus formation over local graphs, right? So I have now two timescales that I've introduced. And then at the third time scale, which is again the one that we're trying to extend and make as long as possible because we don't want to go up to the server, we want to minimize the amount of time we do that, is the global aggregation. At that point, if all of these local clusters have been synchronized, so all of these devices have the same model, all of these have the same model, all these have the same model, the server only has to choose one of those nodes then to get the representative model. It doesn't have to get the information from all of them. So I have an n times advantage, where n is the number of devices roughly in each of those clusters in terms of my upstream communication by doing that. But then we have also these three different timescales that we have to be able to orchestrate over, right? And so we first look and we try to formalize, what's this local model aggregation process. In machine learning, we have a global system objective, which is to minimize the global loss. So this W here represents the set of parameters in the neural network, all the weights on all of the neurons throughout the system. And this D of T represents the global data set. So across all the devices in the system, I want to find the model that's going to minimize the loss, right? Basically on the training data set or some regularized version of the loss, whatever it happens to be, whatever's the global system objective. We're just assuming that it's some form of machine learning, and therefore it has some parameters, it has a data set, and it has a loss function associated with that, okay? And so, but each device individually has its own set of data, and we have to do this in a distributed way. So as we start to formalize the local aggregation process, we divide our training process into a couple of different update intervals, and then we look at what does the local update look like, what does that local aggregation process look like at any given time. And then we perform these, as I mentioned, this consensus process, consensus formation to do these aggregations. So after the local updates, right, so we execute a gradient iteration, means we drift away from each other slightly, our models drift away. Then we want to pull them towards whatever the center point is, whatever the average is between all of those, right? And we're going to do that through some finite number of consensus rounds. And in each consensus round, just to interpret the math here a little bit, what's happening is I am taking what I get incoming from all of my neighbors, and I learn what, say, your model was, and what your model was, and what your model was, but not everybody's model, but just my local neighbors' models. And I'm going to take some portion of them and do a weighted average of what my existing model was. So I'm going to tweak the model a little bit that I have. And you can show using cooperative consensus formation literature, gets into some matrix algebra theory, you can show that this process will eventually converge, as long as your graph topology has some set of properties. We will eventually get the actual average of all of those steps, right? And then between these consecutive updated intervals, that's when we're performing a global aggregation, okay? So one of the first things that we showed back in a paper we wrote in 2022, and I have to mention this, and I hope it doesn't sound like bragging or boasting, but we did just find out that that paper won the Transactions on Networking annual Best Paper Award that they give out. So we're very excited. We just found out yesterday. So thanks. Thank you. I was so excited about that. But so at least it shows, maybe you can go read it. I don't know. I mean, some people have read it. Maybe you can read it then. But within this local model aggregation process, we have multiple degrees of freedom potentially. We have a set of consensus rounds. We have a set of weights that we use to do this synchronization process, and so on. And so when we look at all these different metrics, even if we don't optimize the process, just adding in these consensus rounds, it's one of the first things that we showed in that paper. Just adding in these consensus rounds can really increase the amount of accuracy you can get compared to, say, an upper bound where we're just fully centralizing everything and all the training, right? You can see that as we increase the number of local consensus rounds here, each of these steps corresponds to whatever the global model was. So we're only doing global aggregations this often. So we're only going to the server like once every, 5% of the time, basically, as we are in this central case where we're going after every time step. You don't get exactly to what you would get in the centralized case, but you still get, a pretty nice bump up, and eventually it'll converge to the same point. But it's a trade-off, right? There's a trade-off relationship. This is much more energy efficient than this is. It's like 20 times more energy efficient, right? There's another trade-off though, because as the data sets become more heterogeneous, so as the data, as all the individual device data sets are more different from one another, it becomes harder and harder to just have local synchronization. You need more global synchronization in that case. So we have to understand the level of data heterogeneity as a key objective that we need to optimize over in understanding what these trade-offs are, okay? So we ran through and we can characterize the convergence behavior. I won't go through any of the math here, right? But there's a lot of cool math in that paper that we did. And based on that, we can build a control algorithm. I showed this slide before, to get really nice improvements in our energy cost and delay relative to centralized baselines and federated learning baselines, right? Depending upon how efficient the energy is in the D2D communication. So basically we want to be below this line here. So in some cases, when D2D energy actually is more expensive, right, it may not pay to do this decentralized version, but in a lot of cases, right, it's like as long as your device to device is like 15% of whatever your device to server is, which generally will be the case, you can get a lot of energy efficiency advantages. And I think I'm just about out of time here, so I'll just leave you with just a thank you and some of my contact information here. And just special thanks to a lot of some of my students, my former students and postdocs, and collaborators who were instrumental in making this work. So thank you.
Yeah. Thank you, Professor Bringham. And any questions from our audience? Yeah.
Thanks. It was a very nice talk. And I have maybe first a comment and then a question. So I think, as you might have, well, a lot of people here have heard many different viable options for quantum computing here in the future. We have ion traps, we have photonics, we have Rydberg atoms, and all of them eventually might need to talk to each other, very much like this fog learning. So first I would encourage you to maybe, like, since you're an expert, we might need experts in the field to do that. And second, maybe you have some expert advice or opinion on how that might work, because these are different devices that are very different infrastructure. What's the best thing to integrate those?
So I think that it's a great question, and it's one I've thought about. You know, I don't by any means consider myself to be an expert in quantum. I rely on the experts for that, but I'm certainly very open to collaboration opportunities and all of that. It's part of the reason why I was very excited to be part of this summer school, and also our Elmore Center that we have in the crossroads between quantum and AI. I think there are some processes we can probably just reuse, you know, even from just the traditional like wireless space, in terms of like protocols that are governing how these devices maybe communicate, like you know, at a higher level, not at the physical layer. That's where the quantum gets introduced. So maybe higher layer, like the MAC layer access, right? Like, so maybe we can bring in some of the random access schemes that govern, say, Wi-Fi and how Wi-Fi protocols work, before we get down then to the physical layer, where we use all the really cool quantum stuff that you guys are doing. So I think there's some of those modularization aspects that we can probably layer in there still. But ultimately, I think that, you know, and say some of these problems, right, like where I start to think about it is when I go to, let me see if I have an equation here that would make sense. Well, I have a graph here. Okay, so when I think about it, it's in this stage here of these objectives that you have, in terms of understanding what's the training time delay when I'm communicating with quantum, right? What's the network resource utilization when I'm communicating over quantum? There's probably great reductions you can get, I imagine, right? And so integrating those models into these modules that I have here, I think would bring up some really interesting questions, right? So yeah, that's where I would leave that. I think it's a really good open question. Thank you.
Nice talk. I have a million questions. I'm a physicist. So
I probably don't have any answers then.
So it sounds like one of the reasons you're interested in this is the energy efficiency.
Yeah.
Okay. And you're kind of pulling the energy cost from way upstream in the cloud down into the fog, that sort of thing. To do that, you have to be deploying your software somehow farther downstream. Yeah. How do you get all those permissions to do that? I mean, am I going to be having to tap little, yes, I'm going to allow you to run stuff on my phone, and then if you run stuff on my phone, are you eating my batteries?
Ultimately, yeah. So the way to think about it, you already have a lot of intelligence applications, say, on your phone. So, you know, anything from your health analytics, that if you have like a smartwatch, or just anything else that's running along your phone. We're not adding anything from that perspective into the learning process. Like, a lot of what my research assumes is that your phone's already trying to do some kind of machine learning, okay? And so what I want to try to do is then reduce the energy consumption that's required with that. So the permissions wouldn't be really to download software to do the machine learning, as much as it would be like permissions to, say, have us share your model, right? And so I wouldn't eat your battery from the software perspective as much as it would, I think, try to prevent eating your battery. But it's actually a really good question. It's something maybe more of an engineering question that I need to think about in terms of all the different software modules that are running. But ultimately, we want all this to be actually fully distributed, so it wouldn't always be going upstream, like starting at the cloud and filtering down to you, right? So I think there are a lot of different energy costs, right? There's a cost of just running the models on your phone. There's the cost of communications as well. So these are all things that we try to integrate into the model and trade off with your quality of service, right? So ultimately, like say to get a more intelligent, maybe there would be like, one of the things I've envisioned is there's different like service qualities. Like if you're willing to tolerate maybe a more coarse granular model that maybe only, an example, if you only care about differentiating between cats and dogs, right? I can probably work with a much smaller model on your phone that would be much less resource intensive. But if you want to know, is it this type of cat or is it this type of dog? What are the colors of its eyes? All this stuff needs to be more complex. You just have to kind of accept that and be willing to deal with some of the energy costs. But then that goes also back to the manufacturer, right? I mean, we're building in West Lafayette, we're building a bunch of super semiconductor manufacturing facilities now, right? So at least we're creating jobs, I guess, in that sense, because you have to make things more energy efficient too. So.
All right, let's thank our speaker one more time.
Thank you.
Okay, so our next speaker going to be Professor Kaushik Roy. Professor Roy is Edward G. Tidman, a junior distinguished professor of electrical and computer engineering at Purdue University. He received his Bachelor of Technology from Indian Institute of Technology, Kharagpur, PhD from University of Illinois at Urbana-Champaign in 1990. His current research focuses on cognitive algorithms, circuits, and architecture for energy-efficient neuromorphic computing, machine learning, and pneumomatic devices. Yeah, Professor Roy.
All right, thank you very much. So what I'd like to do today is talk about cognitive computing, but really from sort of the robustness and security challenges point of view. Initially, the last time I gave the talk, it was more on the in computing side of things, learning, neuromorphic computing. So this is going to be slightly different. We all know that, let me see if it works. Yeah, deep learning certainly has made a huge amount of progress in the recent past. And you open up any tech news, you see, all these different news items, right? And the one that came out recently was kind of interesting, and it tells you how far AI has gone. Really, AI won an art contest, and the human artists are furious about it. So that really tells you that a huge amount of progress has been made. But certainly at what cost? It's still AI is still a black box. And if you really think about it, sometimes we don't know why it works well, and sometimes why it doesn't. So is there a way of really finding out? And people have been looking at it from different points of view: digital signal processing, information theory, and so on. So the question, of course, is, can I really try to unravel the black box of AI? Sure. Oh, it's not changing? Okay. So I'll have to go over it again. Yeah. I mean, I can start from here, or? Okay, that's fine. All right, so the question, of course, is how do we unravel the black box of deep learning? And can we really come up with more robust learning algorithms? Can we look at the interplay between accuracy, robustness, and efficiency in some ways? And that's what we're going to be looking at. Again, this is a vast field, and I'm going to be really taking a few examples to show some of the vulnerabilities and some of the interesting things that one can potentially do with AI, and and some possible solutions. So if I were to really look at the modern deep learning pipeline, you certainly need some data set, right? And then finally some sort of a deep model, where in the model, basically, during the training time, you come up with the thetas, which are basically the parameters or the weights of the neural network to learn, and you actually have a loss function that's there at the output, and you try to minimize the loss, as in the previous talk we heard. And then in the deployment, you actually have a test data set that's shown here, and hopefully you get a very good prediction out of your test data set. Now, the question, of course, is, what are the possible problems or the vulnerabilities that we have in this deep learning pipeline? So if I look at the data side of things, there's some interesting things. I mean, there could be mislabeled data, and we'll talk about that. There could be actually some data that, long-term examples, people might have poisoned the data and so on. So the question, of course, is, can I really detect such data poisoning or mislabeled data? On the other side of it, if you really look at the training, there are several other kinds of vulnerabilities that I'm not going to be talking about today. Optimization, when you look at optimization, semi-supervised learning, and model architectures, there could be different kinds of optimization vulnerabilities. And finally, after deployment, and there are other issues that one has to really look at. Is it possible that some of these long tail examples are out of distribution inputs or adversarial inputs, and we'll talk about that, would that lead to any problem? And I'll give you some examples of that. And to that effect, actually, we've been looking at each of those areas, and I'm going to focus on mainly the input part of it, and some of these deployment. So to that effect, let me get started with some of these adversarial examples. And you might have seen some of these examples earlier, but just for the sake of completeness, I'm going to talk about some of these adversarial inputs. Now, in general, let's say that I've trained a deep neural network. And I've trained it, and I've trained it well. And I show this macaw. It is trained to learn it's a macaw. And when I show this macaw, it gives you a very high confidence that it's a macaw. Now, what I end up doing is I actually come up with some crafted noise, let's say. And if I have this crafted noise and I add that to that noise to a human, it's still a macaw, right? It possibly, you don't see any changes. However, now my deep learning model, and I'll tell you how I can do that, deep learning model says with 80% or 90% confidence that it is actually a bookcase, and it has no similarities with a bookcase, right? So these are actually interesting vulnerabilities that one can potentially look at. So these kind of adversarial attacks, which are called adversarial attacks, can have catastrophic implications. Think about it that, in driving scenarios, self-driving scenarios, you have an image, the prediction of the image which is shown on the right, but if I have an adversarial image which looks very much similar to that image that's shown there, and then the prediction is that there are no human beings over there. So if that happens, of course, there can be collisions and other kind of catastrophic problems. And these can potentially happen. And I'll give you some examples of it. So the question, of course, is how do I come up with these adversarial examples? It's a good, interesting way to come up with such examples. Now, when we train a neural network, in general, what we do is we actually show a bunch of data. And then at the output, you say, hey, yeah, I've shown a cat. Is it still a cat? If it's not a cat, if it's showing as a dog, there's a loss. And can I backpropagate that loss to the network, update the weights so that a cat is a cat and a dog is a dog? Now, what one can also do is, and interestingly, take a train network. And after taking the train network, which has these the weight parameters which are given, with thetas which are given, what one can potentially do is now you take you can show the dog, and then you forward propagate through the neural network. It shows it's a dog, but intentionally, let's say you try to make that dog to be a bookcase. Now you say, hey, if it were a bookcase, can I backpropagate that loss and maximize my inputs in such a way, right, so that I don't change the weights. I only change the input in some way so that with minimal changes to my input, can I make the dog to be a bookcase, as an example. And that's what you try to do. Given learned parameters which are there, you find some delta 1 through delta n, which are for the inputs, which is basically some sort of a noise that you try to come up with that maximizes loss over the training data. So this time you're not changing the weights, you're changing basically your input, right? And to that effect, if you do that, this basic idea is that, hey, this is a trained network. I go through a forward pass, I go backwards, but what I really do is I don't change the weights, I end up changing the input minimally as possible. And then I come up with that delta, that noise that I just talked about. If I add that noise to my, if I add that noise to my now macaw, that macaw is probably going to be a bookcase, as I shown earlier. So these are really vulnerabilities. The question, of course, is can I really now try to understand those adversarial examples in a little bit better way? And so if I try to understand it, I can try to see, hey, can I draw decision boundaries? And that's what I end up doing in my neural network, that I have these red balls, the blue balls, and the green ones. And I'm trying to actually come up with a decision boundary so that, hey, the red balls, when I have a test input that comes in, a red ball which falls in that sort of hyperspace, I can call them to be, red balls. So now, interestingly, what happens is that these, the best generalization that you can do is the extrapolation of this boundary of these, hypervolumes is a result of the linearity that yields the generalization. But one can potentially also think of misclassification, as I mentioned earlier. So what one can do is one can take some of these examples which are sort of close to that boundary. And if I can push them in some ways, and that's what I was trying to do by adding some adversarial noise, then now blue becomes green, right? And that's what we try to avoid if I can. Now, question, of course, is in that case, can I generalize better? So what are the ways of generalizing better? One way of doing that is that you generate a bunch of these adversarial examples. You take a trained network, you generate a bunch of these adversarial examples, and then you train the network with those adversarial examples and say, hey, the macaw that I had actually become a bookcase. Now I'm going to make this bookcase to be back to a macaw again in my training. Right? And if I can do that, it's in a tedious process. You have to generate a large number of data, data points. And if I do that, then possibly you can get a reasonably good in a neural network for both clean and adversarial data. But turns out that is it possible that I can use something else? I mean, that's a tedious process. And can I learn in such a way that I probably are not going to see some of these adversarial examples? We humans don't really see these adversarial examples, right? So the question, of course, is, hey, can I now take some cues from how we learn and whatever little that we know from neuroscience? So to that effect, people have been talking about the active vision system. And the active vision system is basically a two-stream hypothesis that's usually, they talk about. One is called the dorsal stream, which is basically guiding the functionality. It's also called the where stream. And the other one is basically the ventral stream, and it's called the what stream. We'll go into that, what and the where stream in just a minute. We can potentially think of, and I'll just go into that in a minute, is somewhat like what we do. We can focus on things at a particular object, and it can blur the rest of the things out, right? And then I have rapid eye movements, my saccades in some ways, and then I go from one object to another object. So that's going to be my where stream versus the what. What object am I looking at? So just to go into a little more details, we have the human eye as part of the human eye is called the region called fovea, which captures the most details, responsible for sharp central vision, which is necessary in human for any activity with where visual detail is of primary importance, right? And this is an example of it. I mean, I can focus on a particular area, the fovea, which is all the details are shown there, and the rest periphery around it is sort of blurred. Again, we are not able to change our focal length that much, but then again, if you can potentially think of looking at this kind of diagram shown on the right, the stop sign, I can actually have my glimpse sizes to be different so that I can get various details. So the question, of course, is, and the other side of it, the where stream that you can potentially think of is what's the saccade is. Saccade is a quick movement of the eye between different fixation points, and human use saccades for scanning surroundings and reading, right? So to that effect, and this is actually some of the earlier very interesting experiments done where we can actually track the human eye and see, hey, how things are, how the human is actually looking at different objects. And this is actually 2 seconds of the observation for a particular example that I'm showing here. Now the question is, can I use these kind of concepts, and would that be more robust? And the reason why it's going to be more robust, hopefully it's going to be clear soon, is the fact that, hey, if I now take an original image and I have to train it in a little bit different way, right? So if I take an original image which has a dog and a cat and a human, is it possible that I actually, learn some of these features of interest, in this particular case, the dog, the human, and the cat, using some sort of a global context network? I'm not going to go into the details of it. It could be random also. And then at the end of it, once I've learned these objects, right, and I know the points of interest, and the points of interest can be determined again through saccades, could be random or could be using this global context network, then I can actually look at, starting point could be those points of interest, and I try to figure out what those objects are. And I have also an idea about the relative location of the object so that I can also be able to understand scenes if I need to. So to that effect, let's try to look at what the ventral stream then, in my case, would do. It's basically the what stream, which is the recognition functionality. I can start my glimpse right here as an example. And this is the extracted foveated glimpse at time t1. And then I actually do, try to figure out, hey, that particular glimpse, does it tell me or does it prime my network into thinking it's actually the cat's ears? And if it is a cat's ears, and if I have some confidence in it, then I need to figure out, hey, I need to go to the right to figure out I can see the cat's eye or the whiskers or not. And then I go move down right, see, hey, the cat's eyes in some ways, and then I go further down and say, hey, it is a cat face. Now I can find the whiskers that I'm supposed to, and it is basically a cat. And I can come up with my bounding box for a cat if I do that. Now, using such approach for learning, what one can do for the fun of it, actually, we played it in our lab and looked at a bunch of images. These are all my students, and tried to figure out, hey, where that face of the student is and who the student is, right? So you can actually come up with a bounding box and say, hey, this is this particular person, and where they are, I can start with various glimpses that I have, change my glimpse size, and figure out where they are. Now, that also tells me that what I'm really trying to look at in these glimpses is basically some features. Some features that I'm familiar with, and based on those features, I try to grow my glimpse size so that I can see the entire object. And now, what we wanted to do is also try to see that what it does to some optical illusions. Now, today, if you give an optical illusion like that to a neural network, it's going to be completely confused, right? But we don't get quite confused in some ways. So what is that? I mean, how many of you see that as a rabbit? How many of you see that as a duck? So most of you see it as a duck. How many see simultaneously duck and rabbit? Actually, theoretically, you don't see simultaneously. You have to change your glimpses back and forth before you actually do that. You don't see it simultaneously. So the thing is that, question, of course, is using such an approach, can I now really think about these optical illusions? And again, the basic idea is that we humans also always look for features, right? You look at the sky, clouds you see. Yeah? If you see patches of clouds, somebody says, hey, do you see that human face? Somebody says, no, it's a dog, right? They actually have different points where they're looking at, and their networks are primed to actually see what they are trying to see with those features that they see. Now, if I now try, for example, my glimpse point right here, or I can start here, I'm going to see two different things. To that effect, actually, we looked at this example of a duck and a rabbit. And we have these fixation points, and what I'm showing in the right is basically what the bounding box tells me. And at the end of it, once my network is reasonably confident here that it's actually a duck. Okay? Now, on the other side of it, if I start my glimpse right here, and on the right, as you can see, at this moment, the network is reasonably confident that it's actually a rabbit. So again, trying to really follow what sort of we humans do in some ways, using this ventral and the dorsal stream. And it turns out I can actually look at features, and I can potentially, now look at the fact that, hey, what's going to happen to my adversarial examples? Can I do better with these kind of techniques of foveation saccades with these adversarial examples? So what we ended up doing is looking at and analyzed, again, the adversarial examples and say, hey, in a passive vision system, what happens is that if I do put a patch, and that patch that I put in there is an intentional patch, which is going to confuse this neural network to actually say it's actually not a bird, it's a butterfly. Okay? And then why, it's going to be clear. On the other side of it, what I do in my active vision system is that I can put the patch in there, but I have different points that I start my glimpses at. And it's an active vision system. And if I do have my glimpses at different points, each of those actually tells me it's a bird, which is a goldfinch. But on the other side, if I start my glimpse over there, right, and if I grow it, unfortunately, that becomes a butterfly, right? Why? Because that has some features of butterfly that my network thinks, and then when it has reasonable confidence it's a butterfly, it stops, right? But in an active vision system, since I actually have my glimpses and I go around, I don't see the major object that I end up seeing is basically the bird, and that's why I don't get fooled in a lot of ways. And if it's a video, it's even better. And in general, we end up seeing on videos. So actually, if we do use some of these, as you can see as an example, the initial fixation point variation, the methodology that we have is what's called Falcon, and basically looking at this active vision system. As you can see, that different glimpse points do tell me it's actually a fish. However, if my glimpse starts somewhere here, it somehow gets confused and says it's something else, okay? Because I stop ahead of time. Similarly, other examples of it that, this is basically the fish, depending on, how many, the glimpse, the initial glimpses that I start with. This is basically an ostrich. But if my glimpse line starts here, it basically predicts what it is supposed to predict. But if I start my glimpse here, it predicts something else, and ends there. So with that in mind, what we feel is that certainly human vision systems are quite stable, and potentially one can use such methodologies to actually have less of these adversarial problems. Yes.
Were the adversarial inputs trying to move the focal points somewhere?
No, I'm basically, my eye movements really focuses on certain areas, right? And then I. No. See, what happens is that what I was showing with the human cat and the dog is that you actually grow your glimpse size, right? And try to figure out, you're priming your network. Your network is primed to be able to say, hey, this is my bounding box for a dog. I have enough confidence as a dog, right? In this particular case, let's say if you start somewhere here, it is basically trying to look at something else, gets primed with these features right here, and somehow, based on my training that I had, it basically says something else, and I stop there. But if I do multiple glimpses, then I don't have that problem. Does it make sense?
Yeah, I was just asking if the adversary tries to intentionally move you to look at areas where you will see the wrong result.
Right. In general, but what I was trying to do is that I take a particular image, and update my inputs in such a way that loss for that dog that I wanted to classify as a dog now becomes a bookcase. I try to.
Choose those initial spots to look at it. Right? How do you choose those initial spots to look at it?
The adversary basically is aware that you're choosing those spots.
No. Adversary, I think let's not look at it from the adversarial attack point of view. It's not quite an attack. It's difficult to attack, but you get fooled. Right? That you can actually come up with different ways of doing that. You can basically say that, hey, I'm going to take a cat and make it into a dog. You can try to say, I'm going to take a cat and make it into a bookcase or a butterfly, right? Depending on the laws that I try to have. Because my network has been trained in a certain way, right? And I'm actually changing my loss with my inputs.
Questions about how do you decide where to look, right?
So in general, we humans try to look at it in general, if I give you a large image, there are 3 cats in there. How are you going to do it? I said, hey, find 3 cats in the image, right? The first thing that you do is randomly look at if you can random glimpses. If you don't find it, then you scan. So it's basically your eye movements tells you how you're going to do it. And I can do it randomly in my network. I can do it in a sequential fashion in my network, and I can do different ways. I think it was, it's from, I think one of the data sets, and I don't remember what it is. I don't even understand what it is. Yeah. All right. Now, one other thing is that, just talking about these adversarial inputs, now let's try to look at it from a little bit different angle and say, hey, is it possible that, I can have mislabeled data, right? Can I detect mislabeled data? Or can I say, basically, can I learn completely from, can I learn human faces by looking at a data set which has automobiles? Does it make any sense? Can I really do such things? In other words, if I can really come up with some secure learning in medical field, for example, in a lot of cases, what happens is that we do have a lot of data, but I don't want to share the data. The data can be sensitive, right? But I would like to actually in some ways learn from each other, right? Is it possible that I learn from each other, but not quite share the data? There are different ways of doing that. And Chris was talking about some of this, I guess federated learning or distributed learning in some ways, and I can, learn using my, the derivatives that I actually propagate. But is it possible that I actually share a data set with you, and it's a sensitive data set, and I don't want to share it, but I want you to learn? In the medical world, that happens a lot. In the military world, that happens a lot. We were actually working with the British Army and the and the US Army. They wanted to share some learning, but not the data. So is it possible to do that? So that's basically a challenge. So the question, of course, is, a simple example could be, can I learn, handwriting digits from images of places? It's an interesting question to ask, and we'll try to see, can we do that? So here's an example of some private images. And I'd like to learn the faces of these private images, and I want you to learn too, but I don't want to give you the data set. So is it possible that I give you a completely different data set that you learn from, okay? But you still learn these human faces. So I give you a public image of places, and this doesn't even look, I mean, there's an aeroplane, as you can see on the corner, right? It doesn't even look like that original data set. So, hey, can I learn from there? Now, this one is actually a little bit different. The last one was bioplausible, but this one, I don't know if it's bioplausible. We can't possibly do that. We can't learn these human faces from possibly these airplanes and all. So now the question, of course, is, hey, is it possible that I take these two images in some ways and synthesize and come up with a synthetic image which looks very much like this? Okay, it's not much different from this image. But if I now give you this image and I say, hey, with the different labels, properly labelize it, hey, is it possible that I learn this? So the basic idea is that they have to be these two are visually very similar. This is visually dissimilar. And this is what I'm going to be. That's my private data set. I learn from it, but I give you this data set to learn from with proper labels. Okay, that's the idea. Or not this one, I give you this particular one. All right, so how can this be achieved? So one simple solution, what one can do is it can, is to directly use the public images. Or in other words, I have trained my network, okay, that's myself, and I have trained it on the private images. And after that training, I actually take my public images, okay, that I have, and I go through my network, forward propagate to my network, and I get soft labels for these human faces. So if I take that and directly give it to you, these public images with the soft labels, you're going to get some sort of an accuracy. And that accuracy turns out is not too bad, but it's not very good either. So in other words, what I'm trying to do is, how is learning possible in this case? By really transferring the decision boundary from the network trained on the private image to the network trained in the public images. Okay, just 1 minute. And then what one can potentially say that, hey, I have private data, I have private data, private class 1, private class 2, and this is the decision boundary for that. I've really done nothing and take that public data set with the soft labels, and then my data lies here. Okay. It turns out it actually does a reasonable job, not very good, but a reasonable job. But if I go further now, is it possible that, take that data set and really perturb this sort of input images, which is my public data set a little bit, so that I can move things around better. And I can now learn better. So to that effect, I mean, this is basically just taking directly the public images and not doing anything. What we can see is that for, if you want to learn these handwriting digits, right? If you align it properly, right? As I mentioned earlier, with that tiny ImageNet data set, then you can actually get some accuracy, but not high, not very high. It is possible to get very, very high accuracy on this kind of MNIST data set. But if I now can do something else, I take this private images, I train my teacher model, right, which is basically my on the private images with the proper data that with a private data set. And then what I do is I take the public image, okay, and I get soft levels, as I said, mentioned earlier, and then I perturb these inputs, just like what I did in the adversarial case, right? In adversarial inputs, I perturb those images. Now I'm taking these public images, I'm perturbing those images to make it look like, or at least to be classified as the private data set. And if I do that, turns out it can actually get very good accuracy. So now if you really look at this MNIST, this is basically the trained, the data set that I'm playing with. We actually looked at various different public images and tried to say, hey, how good is it going to be if I use these public images and try to learn MNIST data set as an example. As you can see that they actually end up doing quite well. Okay? And it's actually, you can almost give for learning these public images, you can actually give those. Huh? So another question that you might actually have, and I'll go back to you, but another question that you might have is that, hey, rather than public images, can I take random images? Okay, and just by taking random images, by perturbing those random images using, the approach that I mentioned, actually what we do is we actually try to use batch normalization and try to map that. Can I take that and learn? It turns out you can, but it's not very good. With the Gaussian noise, just initially you can get something like this. But for MNIST you can learn, but for these other data sets, it's actually difficult to learn. Yeah. Okay. Yeah, you can, but you're not going to get really good accuracy in most of these cases, but you can learn some. But you have to perturb those images. So basic idea that I learn, but when I perturb, I try to match the batch normalization statistics of those private images and perturb those input images so that I can match that batch normalization statistics. Now, the final thing is that another one on the mislabeled data. So if some data is mislabeled, can I detect it? Can I say, hey, somebody perturbed my data set, put in, instead of a cat, it puts a dog. Is it possible to do that? And can we detect and remove mislabeled data? And this is actually, we can be presenting in ICML this year, but how do you do that? It turns out you can look at the curvature of the data with the loss. Okay? So now, in other words, if I look at the curvature of the loss with respect to the input data, and interestingly enough, high curvature means in some ways that that particular data probably doesn't belong to that distribution. Okay? But a low curvature after training really means that it probably falls within my distribution. Now, if it doesn't fall, there are two possibilities. It could be a high tail in a long tail distribution. And if it's a long tail distribution, it's almost like, you have learned red apples and you've only seen one, green apple. And then you've sort of memorized it. There's a difference between memorization and generalization. So you memorized it. Now that memorization is going to give you a high curvature. Also, if you think about it, if I mislabeled that dog to be a bookcase now, mislabeled it, then of course there's going to be high curvature for both bookcase and the dog for those cases. So I should be able to, in some ways, detect it, and then theoretically, what one can show that that happens. So conceptually, I probably don't have much time, but what can look at these curvatures and I can, figure out, hey, atypical samples in terms of the loss versus the input space look somewhat like this. Typical samples looks, more of a flatter minima. So by looking at how the minima is a flatter minima or not, and looking at the curvatures, you can actually potentially say, hey, am I memorizing? Are there mislabeled samples? And so on. I may not be able to distinguish between a mislabeled sample and a memorized sample, but the possibilities are there that I can say that those are the tail of the distributions. How do you calculate curvature? I'm not going to go into the details of it, but it's a little compute intensive. But if you do, calculation of these curvatures for each of those inputs, it turns out that you can actually figure out, hey, those are, what kind of inputs they are. Just to give you an example of it, if you take this data set, on the left side of it, it's actually from, in this data set, I mean, you can see that on the left side has low curvature samples, on the right side is high curvature samples. And in fact, some of these samples are not sort of understandable what they are. You can also look at, for example, MNIST data set as an example, and we intentionally included some examples which are mislabeled samples, like, as you can see, these are 3s, but this is a 5. The question was, can I detect that my data set has these problems? And in fact, indeed, it actually does figure out what those problems are. Similarly, in a fashion MNIST, I'm showing, highlighting some examples, and these are basically present in the data set, that some trousers are mislabeled as something else, as I'm highlighting there. So these are actually, again, mislabeled in some ways. Similarly, in CFAR 10 also data set, there are actually mislabeled samples, high curvature versus low curvature samples I'm showing. They're mislabeling. A good number of some of those are mislabeled. Now, the final question, and I'm not going to go into the details of it, the final question is, hey, can I unlearn some of these mislabeled samples? Or if they're corrupted samples, can I unlearn? Anybody has seen the movie Eternal Sunshine of the Spotless Mind? So that's what you're trying to do. Selectively unlearn. No, is it bioplausible? Don't know. But hey, can I do that? So it's, in some ways, it's basically the eternal sunshine of the spotless network. Okay. So can I can have mislabeled data. Can I unlearn, rather than taking this new data set, removing those data, can I really take this network and just unlearn those things that I've learned? So this is the actually interesting part. I'm not going to go into the details of the mathematics of it, but if it turns out that if I can learn in an orthogonal direction to what I have learned, then I can change my weights. So is it possible that I use that concept of properly projecting the gradients and learn or change my weights in an orthogonal direction to where I have learned, then I might actually be able to forget that. And those particular things which are some features which are specific to that particular object, but might exist in other objects, so the commonalities are not. So by actually showing that you learn in the orthogonal direction, or actually change your weights in the orthogonal direction, you can actually do that. So with that, I know that I've taken some extra time, but just wanted to give you an example of taking a 10% corrupt data. This is my clean data set, okay? And this is how the boundaries are between the red and the green, right? But if I corrupt my data, then it's might have learned it this way. And can I really take this corrupt, this input, and correct it? And Verifix is the technique that we developed by using actually changing some weights in the orthogonal direction of learning. That if you can do that, then you can unlearn and sort of go back to what your clean data set should do. All right, with that, I'm going to be stopping here, and parting thoughts. I still think there's a lot more things to be learned. Deep learning is still a black box, and trying to figure out different techniques to see how we can try to make things more robust. Right, let me stop here.
Such an interesting talk. Any questions from our audience? Yeah.
Thank you, Kaushik. The question that I have is, so this is for learning up of of image pattern and image recognition, and in that context. However, my question is, can it be broadened? For example, if you look at a process, let's say an assembly line, a data coming from an assembly line. Can you look at the data and learn up, okay, that's what is going on with the data, that's what is going on with the assembly line, that process is wrong, and then broaden the scope?
Yeah, I personally believe you can. Basically, what we're really saying is that, hey, some of those, things that we're looking at here is basically looking at the distribution of data, and if I can try to figure out if it fits in. That's one possibility. But then again, the thing is that you might have, if you look at the process, if you trained it, you said, hey, this is what I see. I train it on that. And one of the other things that you can do is that, hey, you can take some failures that you have seen and you can relearn on those failures or incrementally learn on those failures that you have seen. There's an area called meta learning and continual learning, so you can do some of those.
Thank you, Professor. Going back to your glimpse point, is the glimpse point determined through some algorithm, or is the glimpse point determined somewhat arbitrarily? In other words, is there some sort of magic symmetry points that can be determined algorithmically, or is it just kind of luck of the draw for every image?
Yeah, both in some ways. The thing is that in general, what one can potentially do is, I was showing this context network and I say, hey, what are the points of interest that I'm going to be looking at? And for that, I need a trained network. Okay? I have to train a network with which we call the global context network, which is going to tell me with very low resolution, what are the points of interest. Now, another way of looking at it could also be, for example, I was putting that question, hey, can I find out 3 cats in this large image that I have? And in general, what we do is we try to find out those cats, right? And randomly to start with, because it's maybe a large image, randomly I try to see if I can find. And if I find 3, that's fine. But if I don't, then I can go and look at. But again, also we can potentially use a context network in that case too, but that training sometimes might be difficult, or I might have to do sequentially in my saccades. Yeah.
Oh, thanks for a wonderful presentation. The thing that you mentioned about merging different data sets, especially in a secure and safe environment.
Not merging.
Oh, sorry?
Not merging.
Yeah, but just
I'm
working.
I'm giving you a data set to learn from,
Yeah.
which is dissimilar to my
one.
private data set, but you learn the same thing.
Yeah. So I'm actually trying to build an idea on that. Like, why do you see an application? Because one of the ways that people do this domain adaptation, for example, is to merge through different embeddings. Because if you don't have the data set, but if you can get the embeddings, which might not be as private and will be more anonymized and everything, people do that. And there are also applications of that in LMs, for example, as well. Like you can just, instead of merging different LMs, you can just merge the different embeddings itself, and then mixture of expert model to apply to gain expertise just from the embedding itself and not touch the data set at all. So do you think that that's a viable option in this case as well?
Yeah, there are different options. There are absolutely different options possible. What I wanted to show is that certainly you can learn from a completely different data set, which you may not be able to derive the original one from. So differential privacy is also important, right? Can I really make sure that I have that along with this? So that was the idea. One is visual dissimilarity, and I should not be able to generate it from my data set.
Thank you.
Okay, thank you, our speaker, one more time. We're gonna have a break for 10 minutes, and we're gonna coming back at 10:45. Thank you. So everyone, please be seated, and we will start very soon. All right. So our next speaker is Professor Erica Carlson. Professor Carlson is a professor of physics at Purdue University. Professor Carlson holds a Bachelor of Science degree in physics from the California Institute of Technology, as well as a PhD in physics from UCLA. Professor Carlson researches electronic phase transition in quantum materia. In 2015, she was elected as a Fellow of the American Physical Society for theoretical insights into the critical role of electronegativity disorder and noise in novel phases of strongly correlated electron system and predicting unique characteristics. Professor Carlson has been on the faculty at Purdue University since 2003, where she was named as a 150th anniversary professor in recognition of teaching excellence. She is a founding member of Innovation in Quantum Pedagogy and its relation to culture. Her latest work popularizing science can be found at youtube.com at the Quantum Age. Please welcome Professor Carlson.
Thank you for that introduction, and thank you for the invitation. I'll be telling you about universal features of emergent electronic fractals in quantum materials. We are pleased to have several funding for the research side of things, several funders, National Science Foundation, Department of Education, Department of Energy, Research Corporation, and Fulbright. And also for the outreach side of things, Department of Defense, funding the YouTube channel. My theory collaborators on the research side include Karen Dahmen at University of Illinois, and a lot of my students, some of whom are here. If you're one of my students, raise your hand real quick so you can talk to Yushin if you have questions. I think Shashank is also here. Our experimental collaborators are in the group of Jennifer Hoffman at Harvard University, Ricardo Comyn at MIT, Alexander Zemera at ESPCI, Dmitry Bazov at Columbia, and Ivan Schuler at UCSD. Now, the first thing I want you to think about, because I want to think about quantum materials, and I want to think about what quantum materials can do for us. What we mean by quantum materials is something where we're going to take the quantum properties that are typically locked away at the atomic scale or smaller, and we want to bring those nice properties to the forefront of a material where we can control them and use them. So we're about getting new capabilities, okay? So I'm going to give you an analogy about what new capabilities are like. And let's say, for example, we have an artist who gets to only paint in monochrome, okay? So this artist might paint us a picture that looks like this. We would call it black and white, but really we mean monochrome, it's grayscale. And it's a nice image, there's nice contrast in there, you can see some beautiful things. But what if I give this artist now a new color, okay? Now I've given this artist red. Now they have a little bit more dynamic range. We get a little bit more interesting picture. And now I'm going to give this artist a new color. Let's give them yellow. What can you do now, right? I mean, can you imagine being an artist and all of a sudden you have a new color? Well, you can mix those colors. So now not only can this artist paint in light and dark and in red and in yellow, but they can mix the red and the yellow and they can get these other colors in there appearing like orange, for example. And now if I give them blue, I can get the entire, range of vision that humans can perceive, and I get all the colors now, right? So now that I have blue, I can mix the blue and the yellow, and I can get green, and I can mix the blue and the red, and I can get purple. So I fill everything out once I get all these capabilities. So it's a little bit like this with quantum materials. Every time we invent or discover a new quantum material, there's a new capability that comes along. And it's like we're handing a new pigment to the inventors who invent new things with these new capabilities. Or if you like Legos, you could think a little bit like, it's getting a new Lego piece. How cool is that? What more can you do? So quantum materials do this for us. They give us new capabilities. And within these quantum materials, we get new types of particles, actually, that, some of them have an analog in the natural universe, and some of them have no analog in the natural universe, and some of them we think might exist in the natural universe. We just haven't found them out there yet, but we can make them in quantum materials. So for example, whereas the natural universe, we have this set of particles that you would know as the standard model, right? We have quarks and gluons and electrons and muons and photons and things like that. We get to have a whole new set inside of quantum materials. We can have holons and spinons and Majorana fermions and vortices and magnons and Dirac fermions and on and on. There's more than I've shown up here. And we're at a fabulous place in the history of human discovery. We used to go out and sort of ride off into the sunset and discover what's at the horizons of what's at the frontiers of human knowledge. We're at a new place where we can design materials from the ground up, atom by atom sometimes. Okay, maybe you've heard of like those van der Waals materials where you have little layers. You could take the layers and stack them and twist them and things like that. We can also design things atom by atom. So we are not just discovering what's at a frontier, we are creating this landscape and this new frontier as we go along. So it's a very exciting field to be in. I'm glad you're here. There's a lot to do. So we have these new capabilities inside. It's also a little bit like new universes because we have these new particles. If you'd like to know more about that sort of big adventure of what all is going on in quantum materials, I hope you've already pulled out your phone and snapped my QR code, because that's about, that takes you to the YouTube channel called The Quantum Age, where I have several videos there. More will be coming about quantum materials, but also about just basic quantum concepts with no math. Okay, no math, and yet correct. That's my goal. I would not be telling it to you if I didn't think it were correct. And I also have other scientists and engineers who help me make sure that it's correct before I say it. So if you want a place that either yourself can learn about basic quantum things in an enjoyable way, or you want to be able to tell your friends and family who don't work in the field what in the world you're doing and why it's so exciting, I hope you'll point them to the YouTube channel. So here's the piece of this a large piece of this that we work on inside of quantum materials. We started to notice, so we're a theory group, okay? So that means that we write down equations and we run computer codes and design computer codes in order to make statements about the physical world. And I'm showing you here some data sets, okay? Not taken by us, we're not the experimentalists, but taken by experimentalists in the field on various types of systems, okay? And you don't need to know exactly what the data sets are doing, but what I want you to notice is that there's structure in the images, there's spatial variations, okay? So oftentimes, these new materials, rather than the electrons going in them uniformly, like if I think about how are electrons distributed inside of a semiconductor that you would commercialize, or inside of the metals that we use for wires to carry current, they spread out evenly, a little bit like liquid filling a container. This is really different, okay? So here, the electrons themselves are doing some strange thing, all right? So where either the electrons themselves or the properties of them are inhomogeneous. There's spatial textures that are going on. And so the first two in the upper left are high temperature superconductors, cuprate superconductors. The ones on the bottom are metal insulator transition materials. So the two colors you're seeing are metal and insulator. Here, what you're actually visualizing is stripe orientations. It's something that coexists with a superconducting phase. There's these little train tracks that switch direction, and here's a visualization of the direction of those things. This is a phase that's not entirely understood in strontium iridate. There are two different components is the main thing you need to know, and they make an interesting spatial texture. These are antiferromagnetic domains. A point I want to make with this is that the electronic properties are not homogeneous. There's spatial structure there. And so the electrons get very clumpy. And it turns out that our ways of organizing how these things are behaving are not necessarily tuned to these clumpy kinds of things. And in fact, we need to think in terms of phase transitions and phases of matter, but things that are just on the edge. So you've heard of lots of phases of matter, I'm sure. You've heard of solid, liquid, gas. You might probably throw in plasma or liquid crystals if you're really getting into it. But electrons inside of materials have their own phases of matter and phase transitions. So for example, a metal behaves very differently from an insulator, behaves very differently from a ferromagnet, and so forth. And there's lots and lots of these different electronic phases of matter. So what you're really seeing up here is, here you've got two different phases coexisting, right? You've got a metal and an insulator distributed throughout. And here I've got two different directions of these little train tracks called stripes in two different directions, and things like that. So we need to think in terms of how do I get from one phase to another, for example. And there are actually two types of phase transitions, broadly speaking, all right? You might hear the language first order and second order phase transition. The more modern way to classify these is discontinuous and continuous phase transitions. It turns out that everything you have physical intuition with a phase transition is in this class. Everything you've handled in your everyday life is in the discontinuous phase transition or first order phase transition category. If, by the way, if you come up with a continuous phase transition that either people see in their everyday lives or I can tell people how to make in their kitchen or in the garage, let me know. I'd like to be able to tell people. But you're used to water, basically. Water boils and freezes, okay? And as it does so, it has a latent heat of transition, okay? And you're never confused as to which phase you're in with water, right? If I give you a glass of ice water and you look at it, you're not wondering, well, where's the liquid and where's the solid? It's really clear. The ice is here and the liquid's there. Nobody's confused. In the other type of phase transition, if you have what's called a continuous phase transition, you have a continuous change of all the physical properties. Nothing ever jumps discontinuously. So for example, here's how a magnet demagnetizes. So if I take just a permanent magnet, we would call it a ferromagnet. And I watch how the magnetization changes as I raise the temperature. Eventually, if you raise the temperature enough, you get an electronic phase transition where the magnetization goes away. That's called the Curie temperature. And then if you lower the temperature again, boom, the magnetism comes back. But it does so in a continuous manner. The magnetization goes continuously to zero. There's still a well-defined temperature at which the properties change, and that's the phase transition point, but the properties are continuous. What's really cool is that in this type of phase transition, you get all sorts of bizarre phenomena. You get universal properties within different classes. So for example, it means that essentially all magnets you've worked with demagnetize in the same way. If I just show you how it's crashing down at the end, you would not be able to tell me whether it was iron or nickel or cobalt. This part, this shape becomes universal. So that's pretty cool. The other thing that happens is that we get structure on all length scales at that transition point. And that structure at all length scales translates mathematically into what we call power laws. And that translates visually into fractals, and that's pretty fun as well. So let me show you an example of one of these continuous phase transitions. So this is a mixture of two liquids at high temperature inside of the test tube. The water bath around is just to control the temperature. So at high temperature, these two liquids mix together, and at low temperature, they unmix, okay? I think it's cyclohexane and methanol. It doesn't matter exactly what it is because all fluid mixtures unmix the same way. So as we lower the temperature, they're going to unmix, but watch what happens first. You're starting to see weird things happening. You see these little white tendrils at the top. That's the beginning of the phase transition. It's starting to happen. And now those white tendrils, in a nice correlated, fluctuated way, come down, and now they just took over the whole sample. This moment is called critical opalescence. That is the transition temperature. And that white region overtook the entire sample. And now, as we cool even further, we'll start to see the heavier liquids going to kind of run down and gather in the bottom. But that's what a continuous phase transition looks like. Right at the transition point, there were fluctuations. You saw the fluctuations start off at small length scales and then grow and then grow and then grow and overtake the whole sample. And if we had a large enough sample size, we believe that those fluctuations would grow out to however large your sample is, infinity in principle, right? Nobody measures that, but we can talk about it as theorists. So that's pretty fun. And again, if you find one of those continuous phase transitions that I can tell people how to make it at home, let me know. I'd love to be able to tell people about it. So this is called critical behavior. When you get these fluctuations on all length scales, there's no characteristic length scale. And in fact, if you look at the spatially dependent properties, if there's no characteristic length scale, I can zoom in and it looks the same. And that gives you fractals. The reason this turned white, by the way, is because you had density fluctuations on all length scales. Those density fluctuations scatter light. because they're happening at all length scales, they scatter light in all wavelengths, all colors in the visible, and it looks white to you. So let's think a little bit about what fractals mean. Fractals come along with scale and variance. Objects that you touch in your everyday life have a scale to them. They have a rough size. Your cat, for example. How many people have a cat? Anybody have a cat? Okay, your parents have a cat. You had a cat at home. You've seen a cat. How many people have seen a cat? Okay, they have a particular size, right? So when you zoom in on a cat, it looks very different, right? You're not confused between these two images, right? This is pretty clear to you. But this fractal on the right, this is a Mandelbrot set, and I'm just gonna have it zoom in, okay? I did not make this video. This is put out by these guys here. But you can see as we zoom in, you get this sense of deja vu, right? It looks the same, and it looks the same, and it looks the same. And we're just zooming in. So on all these different length scales, you couldn't tell. If I showed you a picture of the original and the zoom in and the zoom in, you can't tell the difference. That's fractal behavior. That's self-similarity on different length scales. It looks the same as you zoom in. And so the question we posed was, gosh, this is interesting. There's a lot of different quantum materials with very different properties where the spatial dependence of the properties has all this spatial structure in it. Is it possible that these guys are actually fractals? So that's the question we started asking. In case you fall asleep during my talk, the fast answer is yes. Okay, there you go. But you can also read the papers to find out how we came to those conclusions. I'm going to zoom in and talk about a couple of these, all right? So fractals do occur near continuous phase transitions, as we saw with the test tube. So the question is this kind of behavior driving why those electrons decided to go into those patterns? And you can sort of see by eye that it is a little bit here that looks a little bit fractal, right? I mean, the edges are not neat, they're kind of wiggly. There's little holes inside of holes and things like that. So it looks like it could have some fractal behavior to it. And I'm gonna zoom in and talk about a couple in particular. So the top one here is a cuprate high temperature superconductor. I am calling it a high temperature superconductor, even though this class of materials, superconducts around 100 Kelvin, which is cold to humans. And it's not, people have discovered higher temperature superconductors, but they only work at insanely high pressures, like 1,000,000 times atmospheric pressure. So nobody's putting those in power grids, okay? These guys are actually in power grids. They're actually useful to us. So that's why I'll continue to call it a high temperature superconductor. What you're seeing here is a visualization of those little electronic train tracks. They run diagonally to the left in the red regions and diagonally to the right in the blue regions. If you want to know how the image was taken, ask me during the Q&A. The data set comes out of Jennifer Hoffman's group at Harvard. And this is a metal insulator transition material, vanadium dioxide. And this data set comes out of the group of Alexander Zimer at ESPCI in Paris. I'll tell you a little bit about these two. First off, let me tell you something intuitive that comes out of this way of looking at the data sets, okay? One of the standard critiques of surface probes in condensed matter systems and solid state systems in general is that if I have a bulk system and I'm only looking at the surface, how do I know that I'm learning about bulk properties, right? If you're just observing the surface, how do I know what's inside? And in fact, you have experience identifying fractals yourself. When you look out of a window, you have only a two-dimensional picture of the world, but you can tell by eye, if you see a fractal, you can tell by eye whether that thing fills space like this tree. It's a fractal because it branches and branches and branches. It has a self-similarity to it. Or whether you have a two-dimensional fractal like this frost. Frost is not filling space. It just grows on the surface of the window. So they're very different objects, right? You can climb one, or as we like to do here at Purdue, you can hang hammocks between, right, the trees, but that's not going to work with the frost. So this fractal is confined to the surface. This fractal fills space. And in fact, mathematically speaking, when we analyze the fractal numbers of this image and of this image, we can tell that this one has the type of fractal numbers that can only come from bulk physics. This one is much more like a tree whose roots reach deep underground, and you're seeing the intersection at the surface. This one has fractal numbers that can only happen in two dimensions. It's much more like the frost. So I'm super excited about that. We have articulated a way for image probes or any kind of surface probe, could be a scanning probe, there's at least 20 different types and a growing number. For all those probes within their own data set, if they see self-similar images, we've articulated a way for them to, from their own data set, tell if they're measuring bulk physics or not. Let me zoom in on this guy and tell you a little bit more about it. You'll have to remind me what time I'm supposed to stop. Okay, all right, thanks. So again, this is actually scanning tunneling microscopy out of Jennifer Hoffman's group at Harvard on BISCO. It's a high temperature superconductor. This particular one superconducts at 35 Kelvin. The data is taken at 6 Kelvin. You don't really need to know all those details. It's just if you're scientifically curious about where we got the image. And you're visualizing here those little stripes. So the electrons are running mostly in the diagonal left direction in the red pieces, and in the blue pieces, they're running mostly diagonally to the right, and you get that out of the data set. So we actually know we learned how to extract several measures out of these images in order to try to figure out, well, are they fractal? And if so, can I figure out what drove the pattern formation? And so one of the things we look at is the Hull fractal dimension. That's the edge. This is the question. If you've ever heard that famous question, how long is the coastline of Britain, or how long is the coastline of any coast, right? It depends on what length scale you measure the thing at, because it has structure on long, medium, and short length scales. And you can see that these guys have structure on long, medium, and short length scales. They're kind of frilly boundaries. The volume fractal dimension, by which I mean a generalized volume, an interior volume, basically is about how Swiss cheesy is this thing. Does it have holes, and do the holes have holes, and do those holes have holes? It's like kind of a cascade. So that's the volume fractal dimension. We take another measure out of here, which is to just count the number of clusters of different sizes. There's one big one. There's several medium ones. There's a lot of tiny ones. And so you make that histogram, and you look and see if you have power law fractal structure in your histogram. And then there's other measures we use, which are called correlation functions that we don't need to go into. But here are the analyses that come out of that. The only thing I want you to see out of this is that when I plot the measures on a log plot, so this one, let's look at the volume fractal dimension, for example. This is the size of the cluster, so how big is it in linear extent? And then this is the volume. Just count the number of sites in a particular cluster. And then plot that on a log plot. I get a nice line over several decades. Okay, so this goes over 3 decades, this goes over 2 decades. And all of these measures, except for that one, have some sort of range where I get something linear on a log plot, which translates mathematically into a power law. So for example, the volume scales as the radius to some fractal dimension. Here, the perimeter scales like the radius to some dimension. Had this dimension been an integer number, like 1 or 2, we wouldn't call it fractal. But if it's in between, we call it fractal. Do you have any questions so far? This is a school, so questions so far? Yes, please.
So there was a recent work on neural network hyperparameter visualization. They apparently found that if you plot that hyperparameter space by being just dense grid search, every hyperparameter, they find a fractal pattern. I'm curious, like, I don't think fractals are like fundamental. Like, so you, first of all, because we work on this field a lot, you find fractals as sort of like golden ratio, something like more general work in where you see them in more often cases, and you have some stability parameters or stability patterns which will exhibit or which have some converging parameters.
Oh, great. Okay. So maybe afterwards send me that paper on the neural network. That's fascinating. We actually in a few slides I'm going to use machine learning to analyze this stuff, so it'd be kind of a fun, turnaround. But you asked about stability. So there's certain fractals that are more stable than others. Yes, and I'll tell you that in a couple of slides. So yes, it's coming. That's a great question. And just hold on for like a couple of slides, and you'll see what I'm talking about. Yeah, excellent. It's going to turn out that there's only a few types of fractals that can happen in these systems. So here's the model. So I was talking about stripe orientation. So we write down a very simple model. Look, there were only 2 stripe orientations in the material. It was either running, diagonally to the right or diagonally to the left. And so we make the very simple ansatz that neighboring stripe regions want to be aligned. If this guy's this way, its neighbor wants to be in the same direction. So the way I write that down as a theorist is I say, well, I'm going to call stripes pointing this way a variable +1, stripes pointing this way a variable -1. That's called an Ising variable. And that's what's represented here by this sigma I, sigma j. That just means are my stripes to the right or are they to the left at a particular lattice site I or lattice site j. And this what I'm writing down here is a Hamiltonian. You can think of it as an energy function. So basically what this says is that, well, I'll sum over the little triangular brackets there mean nearest neighbors. So if I look at little nearest neighbor patches, I want these guys to align. I'll lower the energy. This j is positive. I will lower the energy if these guys are pointing in the same direction. And so I'll allow for some coupling within a plane. So within, these are, I should have said, these particular materials are highly layered. They're bulk materials, but they're highly layered. You can just peel layers off with tape, okay? And so the in-plane coupling we expect to be different from the coupling between planes. It should be weaker coupling between planes. So there's the weaker coupling between planes. And then to model this order, we do what's called a random field. So the basic idea there is that for these cuprate superconductors to work their magic, you have to dope them. Doping is chemical substitution. It is an uncontrolled process. And so where those dopant atoms go has some statistics to it. And so you might imagine that in one region, the dopant atoms have some configuration that tends to drag the stripes one way. And maybe over here, the dopant configuration is different and it tends to drag the stripes a different way. That is, in my model, that's like a local magnetic field on my director, right? This sigma variable that points it one way or the other locally. So the way that comes into the model here is as a local, it's essentially like a little local magnetic field dragging a magnet one way or the other. And then we choose that out of a Gaussian distribution. And so that's how we model disorder in the system. It is a very simple phase diagram. Either you have the stripes all pointing in the same direction. I've called that ordered. They're nice and neat, right? So either the stripes are all pointing in the same direction or they're not. They're disordered, okay? So at high temperatures, you'll be in a disordered phase. At low temperatures, you'll be in an ordered phase. What are all these axes? This is temperature. Along the horizontal axis, I have random field strength. So how much have I doped the sample? Going back in this direction is dimension. So the front two axes are the two-dimensional limit of films. The back two axes are the three-dimensional limit of a fully isotropic crystal. And we're looking at a layered system, so we're really honestly probably somewhere in here. But the question is how important is it? Now here's the thing you need to know. There's all these phase boundaries, and going from the ordered to the disordered phase, the fractals are occurring at the phase boundaries. They occur at the phase transitions. And you saw that you'd get a little bit of that fractal behavior, not just right at the phase transition, but as you approach it as well. It's sort of like the fractals start and they grow, and right at the transition point, they extend over the entire system. But when you're near it, they don't quite extend over the entire system. So it's only properly fractal right at the transition point, but when you're close, you can still see the behavior. Does that make sense? So the fractals are actually all along these, anywhere you see a black line, that's a phase transition. And as you pass through that phase transition, you'll get that critical opalescence that I showed you in the test tube. And the electrons will make these crazy patterns on all length scales. They'll make fractals. And to answer your question about, well, are there classes? There are absolutely classes. And so on each of these black lines, I've drawn an arrow which points towards a green dot. And this is something called renormalization group theory. You're welcome to ask me about it afterwards. But essentially what it tells me is that if I'm anywhere on this black line, I look at that blue arrow and I look at that green dot, if I'm crossing the phase boundary here, I'm going to have fractals of this type. That just tells you the type of fractal you get. It's in the, we call it a universality class. It's in the universality class of the three-dimensional random field Ising model. If you're crossing the phase boundary over here, I look at that blue arrow, oh, it's going to flow to here. I'm going to be at the clean three-dimensional critical point. The disorder doesn't matter. So there are some cases when the disorder doesn't matter. Some cases when the disorder, we say, shifts your universality class, and you get different shapes of fractals. So these red boxes tell you there's basically 5 different kinds of fractals that can come up in this context. Did that kind of address the question of what types of fractals we can get in this model 5? Okay. Yeah. Okay. So this isn't necessarily about stability. Well, actually it is. The green dots are your stable points. The green dots are stable points in there. But this is more about as you raise the temperature on some physical system, what type of fractal are you going to get? And this tells you what type of fractal you'll get, which it's a universality class. It's very closely related to this word stability you're using, but we call it a universality class. I'm happy to talk more about that. Yeah. So basically, the upshot is that in this cuprate high temperature superconductor, in a data set that's tracking these stripe orientations, we find in fact that the numbers we extract, those fractal numbers that we pull out, it turns out that those fractal numbers, and I showed you that on this slide here, we extract 5 different fractal numbers. That set of fractal numbers is like a fingerprint for identifying which type of universality class am I in. Am I in 2 dimensions or 3 dimensions? Did the disorder matter or did the disorder not matter? Did the interactions matter or did the interactions not matter? That whole question is set by these numbers, and it's like a fingerprint for telling you where you are. So that analysis tells us that in fact, these stripe orientations, that pattern is in the 3-dimensional random field Ising model universality class. So it's 3 dimensions, even though they're just observing the surface, you can't get that shape unless you have that pattern going throughout the entire material. Do need randomness to describe it, so the dopant atoms are mattering. The dopant atoms have shifted the shape of the fractals. It matters. Even though the dopants themselves are tiny and they don't have much range of influence themselves, how in the world did the dopant atoms cause long scale structure? It's the interactions. So the fact that I also have interactions between them transferred it into something that's happening over all length scales in the system. So it's this universality class. And there's our theoretical model of it generating, prototypical structures that can happen in that. So this is actually a disorder and interaction driven structure that can happen here. But I think the take-home message when you see structures like that that are over multiple length scales is that when you're doing simulations on the behavior of the material, it's not going to be sufficient to do a single site simulation or even a 2-site. You've got structure going on at multiple scales. So you need to simulate large systems if you want to include these kind of correlation effects. The other strange thing, this is kind of a fun thing of just throw this in. They had different dopings. This is temperature versus doping in the material. There's the superconducting dome. SC stands for superconducting. Our collaborators had 5 different dopings that covered quite a range of the superconducting regime. All their data was taken at 6 Kelvin. They saw the exact same stuff. Every single time they saw the exact same stuff. So these fractals are taking up a huge region of the phase diagram. It's temperature versus random field strength. This is a slice of the phase diagram I showed you before. If I color in yellow, kind of where do I get these fractals? They're on the phase boundary. They're actually in an increasing region as you lower the temperature. Very bizarre. It's a strange model, but that's what happens in a disorder-driven model. So this is the region of fractals, which is actually turned out to not be the expectation in the field. What people expected in a temperature versus something that's not temperature phase diagram was to have the quantum critical behavior show up. Quantum critical meaning I drove some quantum parameter, but quantum critical can also give you fluctuations on multiple length scales, but the region, this yellow region of where you would get that kind of behavior is very narrow in the phase diagram and goes up in temperature. So these are quite different regions in which you're seeing it. So in fact, this broad critical region here that we're seeing, the fact that the fractals are all over the place is a different type. It's a disorder-driven type of criticality. And how these two go together is an open question. How does the disorder criticality, which makes fractals everywhere in the phase diagram, and the quantum criticality, how do they go together or not go together? And my student, Yushin Soon, who is right here in the middle, is working on that. So if you're curious, you can ask Yushin about his latest results. He's still working it out. So when we ask the question, are these guys fractal? The answer for the stripe orientations and the cuprate superconductors is yes and yes. What did we learn? We learned that fractals dominate the phase diagram. And the take-home message for the research community is, well, beware models that don't have disorder, because it turned out that disorder shifted the universality class and the long-range behavior of the material is affected. It also means that you probably need to simulate large systems if you want to try to capture that behavior. Simulating one site or 2 sites or 5 sites or 10 sites is not going to be enough. You actually need large system sizes. So I need to take questions though. So let's do this. Same thing happens here. It's also fractal. It's a fun story. We used machine learning in that case, an alternate technique to identify this one. It also goes fractal. Very interesting stuff. We'll just skip it though, because I want to be able to take some questions for you. We are working with Jeremy Levy's lab at Pittsburgh, by the way, to design fractals inside of quantum materials. So that's a fun thing. And my student Shashank Anand, who's been here, is working on that. If you're curious, you can talk to him. There's my summary slide. We have a lot of references. There's the QR code to the group, and there's again the QR code to the YouTube channel. And I'm happy to take questions. Thanks for your attention.
Thank you for the fascinating talk. Any questions from our audience?
Thank you very much for the great talk. I have a question about the global properties, the long-range order that you get during the fractals. So what can you make out of it? It's because then can you define a topological order of the material, and then can it be used for fault tolerance or something like that?
Ooh, okay. Fault tolerance, great idea. I don't know the connection to fault tolerance. Long range order and things like that. So this is actually, when we talk about how to define a phase of matter in condensed matter systems, you mentioned long range order, you mentioned topology. This is totally different. And so we had to because we were up against data sets that just didn't fit those paradigms, right? So the standard, say, Landau theory of phase transitions would tell you that you need to look for long-range order. Well, that definition of when a phase happens is about long-distance behavior, and it's really about correlations. Is this region acting like this correlation? Are they fluctuating together? Like you kind of saw in the test tube, you could kind of see things fluctuating together. Okay, that's a long-range correlation. So you're looking for long-range, long-time behavior of something to tell you what phase of matter you're in. Are you in ice? Or are you in liquid water? It's a long-range, long-time scale question. And so that's the traditional way to categorize phases. It's failing in several cases. So it's really not telling us the information we need to know about these highly structured cases, right? You mentioned topology. Topology is another way that we categorize phases of matter and phase transitions is by their topology. Here, and typically in those cases, you have to kind of put periodic boundary conditions on to really make sharp topological distinction. So although this is a highly textured thing, I'm not sure we would put the topology language on it. It's really kind of a thing in itself. It's just the idea that look at certain phase transitions, you get structure on all length scales when you're near the phase transition. And the particular phase transition that I showed you, the random field Ising model has a huge critical region. You don't have to tune, you don't have to make fine adjustments to find this stuff experimentally. I showed you it was all over the phase diagram. And that's because, in fact, the model itself, you can see this critical behavior. You can be within 50% of the transition and see 2 decades of scaling. I mean, it's 2 factors of 10 in your log-log plot of that linear stuff. So it's kind of a third way to think about things. Yeah.
Any more questions? All right, let's thank our speaker one more time. All right, let's welcome our next speaker, Jake Douglas. Mr. Jake Douglas is a technical business development specialist at Sandia National Lab, where he leads quantum business development efforts for Sandia's quantum information science portfolio. Jake has a Bachelor of Science degree in chemistry from New Mexico Tech and an MBA from New Mexico Highlands University, the combination of which allows him to both follow his passion for business and pursue his technical curiosities through QIS. Jake works closely with Sandia's QIS leadership to develop game-changing new programs at the laboratories in support of Sandia's national security mission. Jake works for a continuum of business development functions at Sandia, including program development, strategic planning, workforce development, and partnership. When not engulfed in the world of QIS, Jake enjoys challenging new board games, playing various sports, home renovation project, and spending time with friends, family, and his 4 awesome pets. What a warm introduction. Thank you very much.
Thank you. Awesome. So hi, everyone. Like I said, I'm Jake Douglas from Sandia National Labs. In addition to the things that I do there, I also work really closely with the Quantum Systems Accelerator, which is one of the 5 DOE centers where I lead workforce development. And then I also am the chair of the Workforce Technical Advisory Committee of the QEDC. So QEDC's workforce focus group, essentially. So we all obviously are familiar with the things that we want quantum to be able to do, but I like opening up with kind of just a high-level impact slide of where we think quantum is going to be able to go, right? So within sensing, computation, or communications, what are some of the things that Sandia is really curious about? If it's within optimization, how is that going to be applied to our electrical grid or to flight path optimization? If it's communications, how can it help enable our mission there? Things of that nature. And we really think that this is going to have a broad impact across both kind of national security and the economic security side of things. So just to kind of frame the rest of the conversation, these are the types of things that we like to think about. So we're going to shift things up a little bit from the previous presentations, and I'm going to talk a little bit about the broader ecosystem to try to share what's happening across the country. So as many of you know, the National Quantum Initiative was launched in 2018 to really create this all-of-government approach to moving quantum forward across the country. It's called out 3 different government agencies, the Department of Energy, National Science Foundation, and National Institute of Standards and Technologies, to receive a good amount of funding to be able to really accelerate quantum tech development within the country. And so we've seen a pretty significant amount of activity happening since then, with over 500 million invested into each of those areas. In the bottom right here, we can see where these major NQI centers and their affiliates are kind of throughout the US. So it's scattered about. The DOE leads the 5 centers that are all run by national labs. The NSF runs an additional 5 that are run by universities. NIST launched the QEDC, and then DoD has also set up a few labs to participate from their capacity, which is in partnership with NQI centers. In addition to that, we obviously have lots of other efforts across the government where DOE and NSF both have pretty expansive basic research portfolios, things like that, which enable a lot of the stuff you guys do here because Purdue has a pretty amazing program. So because I work with the DOE centers, I wanted to spotlight them a little bit. So each center works together to really tackle different technological challenges across computing, sensing, and communication. The one I'm part of, like I said, is the Quantum Systems Accelerator, which is led out of Lawrence Berkeley National Lab with Sandia as a lead partner. And we're focused on advancing systems across trapped ions, trapped atoms, and superconducting, and really trying to help build the prototypes and co-design needed to move things forward. The other 4 centers are all focused on similar types of challenges. So SQMS out of Fermilab and C2QA out of Brookhaven are working on superconducting qubits. QNext is doing networking and communications, and then QSC, the sponsor of this, led out of Oak Ridge with Purdue leading workforce development stuff, has all the materials and stuff that you've probably heard about from them. So between these 5 centers, there are more than 115 partners. So like I said, they're led by national labs, but there are key roles the academic partners play, the industry plays, things of that nature. And there's more than 1,500 collaborators across both the US and the world. Particularly for this audience, right? So the centers through their combined programming have reached more than 1,000 students. They currently employ over 600 students and postdocs, and they've had a couple hundred new hires since their launch. We're 4 years in as of now, and there's legislation working through Congress right now to give us another 5 as soon as we're done. And it's a really great opportunity to be able to find jobs as you're leaving, to collaborate, to go do summer schools, things of that nature. Like I said, there is over $500 million of funding that went to these 5 centers. And they're really trying to solve major cross-cutting challenges for the field to help move it forward. So for a specific spotlight on the ecosystem, the 5 centers partnered together to jointly host an annual summer school. So it was launched at Fermilab and SQMS last year, where they brought in over 200 participants, kind of across the full education spectrum, to do their summer school. Oak Ridge will be hosting the one this year. Unfortunately, registration is closed. But again, it's gonna host quite a few students at the facility in Tennessee. Next year, QSA, or the Quantum Systems Accelerator, is on the hook, and so we're trying to figure out now what that'll look like. And we're hoping to do a hands-on training type thing to let people go and play with some systems in new fun ways. Additionally, they host faculty development programs, primarily aimed at partnerships with minority-serving institutions, folks who are looking to do capacity building, things like that. So let's say you're trying to get a faculty position somewhere and you want to learn a little bit about what other people are doing, things like that. There are great opportunities there. We also partnered together to introduce quantum to high schoolers, both teachers and students, through QCamp. This year, we'll be hosting 6 different locations for teachers, including Chicago area, Pennsylvania, a few in New Mexico, Colorado, and California. And that's aimed at introducing quantum concepts with no math or prereqs, so similar to what I think our previous speaker is doing. And then one that I would highly recommend is the annual virtual career fair. So that brings together people from kind of across the ecosystem with targeted programming to help connect you guys with people who are hiring, or with people in the field to answer questions about what they do, things of that nature. So in addition to training and working with all the students within the centers themselves, many of you might be working on QSE programs as you're going through school now. There are also annual meetings and workshops, which are great to get engaged in. March meeting and IEEE Quantum Week and things like that. We try to come together and host sessions. And then there are various roadmaps that the teams are working on. Notably, the roadmap for Quantum Interconnects was published within the last few years. So I'm not as engaged with the NSF Quantum Leap Challenge Institutes, but I did want to briefly call them out here, as they do play really important roles in the ecosystem. So there are also 5 of these, and they're focused, across computing, computation, sensing, and some biological aspects of things. And they're led, again, out of places across the country, from UC Berkeley to CU Boulder, UIUC, Maryland, and Chicago. So the third arm of the NQI is NIST, and they launched the Quantum Economic Development Consortium, which is a group of about 240 organizations now that's really seeking to grow and enhance the industrial base in the US, and now internationally with partners from places like Japan and Australia, and the UK. And the way that QDC works is they bring together like-minded individuals across 6 different technical advisory committees, or TACs, which we can see here: use cases, enabling technologies, standards and metrics, workforce, so on and so forth. And these groups are really what get together and try to advance interests in each of those areas. So David Stewart's actually the vice chair this year, and I'm the chair of the workforce TAC, and so that's how we're kind of connected. And we're exploring the ways that industry can connect with students and faculty and others in new ways, because the field is still really new, and we're trying to figure out how we can better make those connections to enable folks to work together better. So in addition to kind of all the government pieces, of course, I have to mention the private investment that's happened over the past few years. So as we can see in the graph on the right, there was investment in quantum companies that was slowly rising. And then in 2018, all of a sudden, we see this huge uptick. So 2022, there was $2.35 billion invested in quantum. And that's just for that year. So think about the cumulative value getting there. In 2023, we saw a bit of a drop to 1.7 billion, which is a 27% decrease. But that still beats the national average of a 38% decrease that comes with like rising interest rates and things of that nature. So the field is still pretty robust. It's doing really well. According to McKinsey, which is where I pulled this information from, there's 261 quantum computing startups, 96 quantum comms startups, and 48 quantum sensing startups. So a ton of energy, a ton of funding is really going into this. And it's slowed down a little bit, but it's still outpacing the market if we're looking at other emerging technologies. So the last thing I wanted to say to, again, try to help set the context is there is a national workforce development strategy for quantum that's released by the White House. And so they go through and they ask, it calls for us to do 4 different things to try to expand the workforce, do it equitably, do it across the full education spectrum, so from high school to postdoc. And so between the centers and the broader ecosystem, there are a ton of efforts going through right now to try to figure out how to build those programs and reach new audiences and do the capacity building that's needed to help meet the future workforce needs. Okay, so enough context there. I wanted to move a little bit into what we're seeing in terms of the quantum workforce needs. So currently, less than half of the jobs posted require a PhD. So it's commonly thought that you have to have a PhD to enter the field. As industry is continuing to grow and advance and things like that, that's less and less and less of a requirement. So in early 2022, we just did a quick snapshot over a few month period to see what the jobs look like. Obviously, quantum is pulling from a lot of different disciplines like physics and electrical engineering and math. And we're starting to see more and more other fields getting pulled in. So be it business or policy or law, biology. From this quick study, we saw that about a little over half were coming from physics, 34% from engineering, 32% from computer science. And as new data is being pulled, we see those continuing to expand out to other fields. So just to give you an idea of regionally where hiring is happening, I showed you a little graphic of where the NQI centers are, and in a lot of ways, that's where a lot of the hiring is happening. So in the blue, it shows our national labs. In the green, it's our academic institutions, and yellow is industry. Yellow is where it kind of breaks that the hiring stats down. But there are, you can see major hubs kind of popping up around the US with strong correlations to the NQI centers and what the government is doing. Again, this was just a quick snapshot. There are going to be jobs in other places. There aren't a lot of quantum-related jobs in the titles themselves, so we had to do some data analysis. So we know there's some stuff missing, but overall, this gives a good idea of what's happening in the ecosystem. So if we're talking about the different types of jobs and how you can get engaged, there is really a really nice paper by Asfa et al. That was released that kind of created this figure that I'm showing here on the left of the number of positions open versus the level of education. And so if we're looking at the bottom of this pyramid, non-quantum engineers employed in quantum companies, you're going to tend to have the most opportunity. You're going to be focused on kind of classical systems, be it software or cryo and fabrication, things of that nature. That's where most of the job postings are seen. As you move up in levels of education to quantum aware engineers, quantum proficient engineers, you're getting more specialized, right? You're going through, you're learning a lot more, you're gonna have more quantum knowledge. And then at the very top are the specialists, right? You have your PhD in quantum related fields. You're gonna be going through and helping build new devices, getting the theory to really enable the field, but that's gonna have the fewest job opportunities. You're very, very specialized. If we look in the right, we try to say the same thing in generalized by kind of roles. So, as a PhD, you're gonna have that really deep knowledge and expertise in quantum specific topics. You're gonna be helping develop the next generation systems, developing all the theory needed for it. And you tend to lead or work with these highly multidisciplinary teams to meet your technical goals. On the flip side of that, if you have your bachelor's, you'll tend to have general knowledge that you're going to be using, which is kind of that bottom of the pyramid. And generally it's in classical systems, right? So like computer science, engineering, controls, things of that nature, with limited knowledge of quantum, right? You need to be familiar with some of the vocabulary and be quantum literate, but you're not going to be expected to know everything about it. And then your master's degrees are right there in the middle, where you have some knowledge of quantum, you're specialized in some classical technologies, and then you tend to collaborate with other teams to help move things forward. So in a different analysis that was done more currently, just in the Mountain West, so this is just Colorado, New Mexico, Wyoming, they did an evaluation of all the open jobs, and they found that only one qualified candidate existed for every 3 current job openings. So there's a little bit of a supply and demand gap already. And they were trying to look at and forecast out, okay, what is demand going to look like in 10 years? And so when they're going through and looking at all this, they found that 80% of the quantum job listing had nothing to do with quantum, right? So 20% of the verbiage, the required skills, things like that, would have something related to quantum, but 80% didn't, right? It's things that you're going to be learning, skills you're going to be building outside of the specific knowledge set. They also found that about 60% of the jobs are hardware focused. For the region, that makes sense. There's a lot of enabling tech companies, think Vescent Photonics, and others who are building cryo systems, things like that. After reviewing all the data, looking at the year-over-year growth of the field, they're expecting to have a workforce gap where right now we're kind of at that 1-to-3 ratio, but in 10 years they think there's going to be a 77,000 job gap if the field continues to take off the way it is. That's assuming that the universities and other programs aren't changing what they're currently doing with workforce development programs, which we know isn't right. Like the Colorado School of Mines is doing a lot to get their undergrads prepared for quantum engineering. New programs are being developed with the support of NSF and the DOE, things like that. But it's still really interesting to see, that's a really big number. When I first saw it, I'm like, there's no way that's right. And then looking at the data, there's something to be said for it. And then if we kind of look at the figure on the left here, like I said, currently 60% of the jobs were hardware focused. And we expect in 5 to 10 years, as the systems continue to develop, that's going to flip-flop, where software jobs or theory jobs are going to rise to the top as more people can get their hands on systems and start playing with them, building out algorithms, assuming we have a good application that we've been able to identify that really drives the field forward. So if we're looking at kind of that future outlook, we also don't know what jobs might actually emerge, right? We're still looking for what quantum can do. We don't have that killer app. There are a number of different things that we think it'll be good at, but there's going to be things that come out that no one was able to predict. We also think that the shift towards being able to enter the field without a PhD is going to continue to be driven down, right? So right now, less than half the jobs require a PhD. In 5 to 10 years, maybe that's 25% or 15%. Again, as the machines are getting more developed, easier to run, we're going to see more jobs opening up to make sure that those are actually being accessible by the broader community. And then last thing, being a business guy myself, there is going to be that expanded need for policymakers, for business support and things like that. So that is an area that's growing quickly right now, hard to quantify, but something that's worth calling out. Okay, and so just to dig in a little bit on the job listing review, so the team looked at what the actual skills in the job postings were asking for. And like it was stated, a lot of them are not quantum specific, right? So the ability to code in Python or C++ or Java, or doing systems integration and systems engineering were the top desired skills that were listed in all of the data that they were looking at. The occupations on the other side, we're really looking at just general electrical engineering, right? It's not quantum engineer, electrical engineer, electronics engineers, or computer hardware engineers. And so again, knowing that it's a little more hardware focused based on the region and the companies that are there, it makes sense. But in a lot of ways, that region and industry has been being driven on the hardware side. So the last thing they looked at were kind of the salaries, what occupations are available, and then on-the-job training provided by employers, right? So a lot of times you're coming out of school, you might be worried that you don't have all the skills needed for everything you need to do. Well, most of the employers are willing to spend anywhere from a few months to a full year getting you trained up on what they need you to do, right? So there's a large commitment from industry to make sure that you understand what's needed for their specialized systems. If we're looking at the salaries, we can see the computer occupations and engineering occupations kind of dominate, but to the earlier points, the business operations, the sales reps, the other positions like that are also showing up with pretty good return for the people entering the field. Okay, and then one last kind of comment on here. So being at a national lab, we're often asked, should I go to industry or should I go to academia? Or, what is it like to actually work at a national lab? And so in talking to some of our scientists, national labs kind of fall right in the middle of the field, where we do both fundamental research and applied research. Publications are important. Most positions will require a PhD, and then you tend to work on really large multidisciplinary teams. So pulling from engineering and physics and math to try to create these next-gen systems in a co-designed way. You guys are familiar with academia, so I don't want to put my foot in my mouth here, but publications are really critical. The fundamental research drives everything, being able to follow your ideas and help solve those hard problems at the very beginning. Most of the positions will require that PhD, and you work within your research groups. Then you go to industry on the other end, and it's very, very focused on creating products, right? Publishing is fairly uncommon. Less than half the jobs are currently requiring PhDs. That's where the major draw is coming in for folks who can bring in their engineering and classical expertise to help enable the systems. You tend to work on multidisciplinary teams, but with very specific desired outcomes. So it tends to be a little bit more demanding on your time, things of that nature. And so there are three just different paradigms that as you're looking to go into the field might be worth thinking about. Okay, so where can you go find jobs? This is something we're asked about pretty often. Within the QEDC, we actually have office hours. So once a month, we bring together people from across our QEDC members. So a lot of industry, some national labs and academia will give 4 hours of their time to be available to students to ask any questions you want, be it how to get a job or let's dive into this specific technical topic, things of that nature. And so one way you can find the job is by going and talking to them, right? Or using the QEDC job listing page, which pulls jobs for all of the QEDC members, which again is around 240 now, which is a pretty good amount of the field. Of course, you can apply directly to the job postings with employers or use hiring platforms like Indeed, LinkedIn, Monster, all that fun. But finding ways to connect directly with the hiring managers, with people who are looking to pull in talent, will increase your odds pretty significantly, right? So when you're at conferences and workshops, putting yourself out there and going and talking to the various companies who might be exhibitors, or making sure to submit that presentation or poster, even if you're a little bit worried that it's not quite there, and actually engaging in some job fairs. As we saw, there is high demand from across the industry, and they're trying to connect with students, but it can be very hard, especially as a lot of new programs are emerging, and they don't have the time, especially if they're startups, to do a lot of outreach. So going through and really carving your own path. If there's a company you're really interested in, reach out on LinkedIn to some of the people who you met at these conferences or that you've seen in presentations, things like that. Don't be afraid to introduce yourself directly. A lot of the industry people we talk to say that's the #1 way that they like to hire, right? They want to meet you in person. They want to see that you're willing to go out on a limb and be proactive. So I'd really encourage you to do that. So I'll wrap up there just with the general overview of things, and would be happy to take questions.
All right, any question? Yeah, for our speaker.
Hi, thank you so much for your introduction to the whole program. I'm curious, when and where is that office hours, and how do we get on that?
Yeah, so the office hours are once a month. I think they're the 4th Thursday of every month. So from 9 to 12 Eastern. We are working on updating the website so it's there, but the best way to get connected for this would probably be through David, actually. So we'll share on LinkedIn, we'll share through other social media outlets to be able to access the registration page. Or if you catch me after this, I can connect you directly.
Hey, Jake, thanks for your talk. Any strategies in upskilling an existing workforce to get them the skills that they need?
Yeah, so there are a number of programs that are currently emerging to try to do just that. The QEDC held a workshop last year in Albuquerque at a community college there to really explore what some of those key skills, knowledge, abilities are for technicians, for reskilling, things like that. So there are some professional development courses like MIT X Pro, things like that to help you get familiar with the field, but the hands-on training, retraining, credentialing things, most of those are being done in-house. I do know there are some community colleges like Central New Mexico Community College that are setting up hands-on learning labs now. And that one will launch next January, to try to bring people in to get that hands-on experience for maintaining vacuum systems or cryo systems, things like that. But that's where a lot of the energy and focus is going right now, is the credentialing, the retraining pieces of things. There aren't a lot of really great large-scale programs that I've seen, though.
You have some data on the required nationality, citizenship, security issues, and at what level they're important, where they're not important, and where you're planning to find the U.S. citizens?
Yeah, no, that's a really good question, a hard one that a lot of folks are grappling with right now. Since we're still at a pretty competitive phase, I'll say with air quotes, there's a drive to try to make sure that there aren't nationality requirements. The export controls aren't put in place because that eliminates a large portion of the workforce where right now that's really needed, right, to move the field forward. So, at like Sandia as a national security lab, citizenship is important. It doesn't automatically disqualify you, but it is much, much harder. But if we look at places like Oak Ridge or Lawrence Berkeley National Lab, places like that, no issues there. On the industry side, a lot of the defense primes, the contractors, Lockheed's, those types of folks, I'm not as familiar with what their requirements are. But again, until a policy decision is made that would require export controls or things like that. I don't think it's quite at the critical level of saying yes or no to citizenship. So I don't know if I actually answered that, but did my best. Perfect.
Yeah. We can see more questions for the panel discussion. Let's thank our speaker one more time.
Where did you work at Sandia? Oh, nice. Yeah. Okay. Very cool. When did you come to Purdue? Long time no see, eh? I know, yeah.
Before we begin, we'd like to encourage all the attendees to come closer. That way it's easier to run the mics if you have questions. So please scoot in closer if you don't mind. Maybe we'll make it a little more intimate within reason. All right. All right, let's get settled in. We have 20 to 25 minutes for a short discussion, I guess. Anyways, some of you have seen me around. I'm Morris. I'm a graduate student with Vlad and Sasha, parts of the organizing committee, and I'm glad to have hosted you guys all throughout the week. So we're gonna just do a workforce panel, focus panel with some of our speakers. We have Jake, who just presented from QSA and QEDC. We have Professor Carlson, who presented this morning, and we have Professor Gerhard Klimek, and we have Professor Thomas Roth. But I think just so we can contextualize the discussion, maybe I'll have the speakers go around and just kind of talk about their main focus of their work and how they kind of got into the field of quantum or QIS, if at all.
Yeah, so I've been working with our quantum group at Sandia now for a little over 5 years, where I came on to help prepare for the National Quantum Initiative. So doing things like partnerships, strategic planning, working with our leadership to figure out ways that we can move the field forward through working with external folks. So I came into it because I had a background in chemistry and they needed someone from business who wasn't afraid of the word quantum. So maybe not a traditional pathway, but it's been awesome working in that capacity and with ecosystem partners to try to bring folks together and reach new communities.
My name is Erica Carlson. So as you said, I'm a professor here. I work on quantum materials, so that's my research that I do. But on the workforce development side of things, I've been just very excited about quantum since I learned about it as an undergraduate. It's the kind of stuff where you first learn about it, and you want to sit up at 3 a.m. with people in a coffee shop debating the nature of reality. And so I've been super excited to become a professor, to get to teach this stuff. On the workforce development side of things, you saw before, I have a YouTube channel called The Quantum Age. Get on there, thumb us up, like us. If you want to get involved with that, let me know. I could definitely use some partners. And that's actually under the banner of IQ Park, which is innovation in quantum pedagogy and its relation to culture. We have our coordinator, Dongyang Lee, right here in the front. So if you are curious about all the activities going on there, please ask Dongyang. So I serve as one of the content experts for that. And so we actually, you mentioned on your ecosystem of the pipeline, we actually go all the way back to middle school. So one of our thrusts is we run teacher workshops. One of our members is an engineering education professor here, Musin Menekshi. And so we collaborate on transferring quantum concepts all the way down to middle school, working directly with the teachers to develop that pedagogy in a way that fits into their curriculum, so it aligns with Indiana state standards. And so we're trying to transform how Indiana public schools teach certain things, that we can just sort of slip that quantum in when kids are still in the middle school ages, because it's a great age group. They're still very excited, and they're not too cool yet to get excited in front of their peers. And you have a little bit more room in the curriculum as far as what's constrained, that you can slip some quantum in there. So we're trying to do it as early. That's one of our thrusts. Another of our thrusts that Dongyang is very involved in is the Quantum Game Club, trying to bring people on campus together, mostly students, but people together to play around with quantum computers. Just give them quantum computing time, and they can literally code computer games on quantum computers and other cool stuff like that. It's just basically getting people in a regime where, like you said, they can just get in there and have fun with the stuff and learn and be creative and take off with it. And then, of course, we have that outreach side of the YouTube channel with some other activities that if you want to know more, Dongyang can tell us about.
Okay, yeah, thank you, Gerhard. So my name's Thomas Roth. I'm an assistant professor here in the ECE department. I guess sort of part of the original question was how you got involved in quantum in the first place. So I started doing that towards the end of my PhD, but I was actually coming from a very classical engineering space, designing software to model electromagnetic systems, and then looking at ways that we could start applying those towards these new kind of emerging platforms, like how could you design a quantum computer better using these kinds of tools. So I worked at Sandia National Labs for a period during that time where, again, I was more on kind of applied electromagnetics. And I took kind of the full jump into quantum whenever I came here to Purdue as an assistant professor, where my research group then focuses on quantum modeling. And I've been very involved in some of the different workforce development efforts here related to some of the credentialing that we've kind of talked about. So getting like concentrations within the bachelor's degrees for saying that these people have kind of a recognized focus on quantum technology. Same kind of thing of the university level certificates for the undergraduate level, and then creating classes to support those things, as well as then now kind of spearheading, I think why I got the mic passed to me first, of the kind of Quantum Hub platform on top of NanoHub that Gerhard has pushed for in such an amazing way over the recent years. And so he talked a bit about that in his presentation earlier in the summer school, but again, we're looking at that as being kind of an area where a lot of you can get involved in both using the content that's getting placed there, but also creating your own content to help demonstrate and let people know about the research you're doing and how it can be understood or learned about using these kind of computational tools on NanoHub, as well as all the seminars and workshops and things like that.
So the reason why I wanted to go last is I wanted to tell you that I'm an outlier on this panel. Actually, I would argue the other three are outliers. If you go into the ECE and look at the wall of shame of the faculty members, and I did that 4 years ago, just before the pandemic. We had 130 faculty, 100 faculty members. We're 130 now. At that time, would anybody wager to guess how many were born in this country? 30 out of 100. With 130 now, I think it's now less than 20%. So you guys are the outliers. I'm the norm. I had the first experience with quantum mechanics probably in 8th, 9th grade, where we learned about atomic models in physics. And in 10th grade, we calculated Schrödinger equation in physics. I love math, I love physics, it's great, but I wanted to be an engineer. Now, the trend that I talked about, having foreigners being on the faculty, is a 40-year trend. When I was in grad school here, it was 40%, 50% were US nationals at the time, 1990. Today, when I came back 20 years ago, it was 85% of the graduate school attendees are foreign nationals, mostly China and India. That is true today. That pipeline is draining up. The best students out of China and India will stay there now. Their opportunities are actually there. That brain drain is stopping. We can't even attract anybody out of Europe, anybody, tiny percentage. And we're doing a disservice to our own nation. I'm an American citizen now. I love to live here. I see how my kids are growing up in a school that is supposedly, whatever, number 7 in the Midwest. I mean, supposedly really good. I go to take them to a sabbatical to Germany. Those guys are 2 years ahead in math, physics, anything. Let's not even talk about languages. So, but we can't here fix what's happening in high school. But if we don't change how we teach, where we are today, we're not going to change the outcome. If 30 years ago, people were video recording, literally overhead projectors as they took notes. They dumped it on a VCR tape and sent it to the people in Indiana for remote students. I'm not joking. It's really true. Today, we send the same VCR tapes really fast. It's the same shit. Sorry. It's one on many, no immersive learning, and you pile on the math, and we teach for the 5% of the undergrad or the 2% of the undergrads as if we want to make them professors. Why can't we teach to the 95% that want to become engineers that are productive? We teach for the few that we want to make professors. I'm sure those gifted people that want to become professors, they will pick up the math and the calculus as they need it. But we make that barrier so high for anybody else that they say, screw it, I'm not doing this stuff. I can earn money right away. So unless we, and I'm looking at all the faculty members here, there's only few, which is also very indicative, that they don't care. They don't care. And unless you actually put money down in your next program and actually say, we're going to put 10% of all the stuff that we do, we put that really in workforce for people in community colleges and in colleges that are not R1s, into R1s, and actually put money down, real money. But whenever I talk to faculty members, they say, well, but if we fund one more research group, we can have more graduate students, and we can write 2 more papers per year for $100,000 to $200,000. But you're not willing to spend $1 million or $2 or $3 or $4 million on a quantum hub and on containers, on content, and take it serious. It's a real problem. That's my soapbox. The soapbox is, unless you change directions, you're going to get the same outcome as you got over the last 40 years. So I'm looking at the leaders that actually can call the shot and actually make a difference. Just like what Orit said yesterday, don't think about yourself or your buddy next to you that needs to have a graduate student. Think about the thousands of students that are not seeing your stuff.
So to kind of expand on that, I think, so Jake, I think you are more, maybe more specifically to Jake. So in the, I guess, ongoing discussions about whether to have a more focused and formalized quantum education pipeline to introduce people in the workforce, is that being considered? Like, what is happening to try and make it more equitable across the board for people to enter the workforce? And also with the emergence of AI and with things like CHIPS Act, where money is also being dumped into semiconductors at like all these fields simultaneously? Is there a fight for resources and talents, and what is all that dynamics like?
Yeah, so big question. I'll have to agree though with if we keep doing things the same way, we'll get the same results, right? So through things like CHIPS and these others, all of them have workforce development components kind of built into it, right? That you're required to do. And a lot of the thinking going on in quantum right now is to reach those new students, those new communities. What opportunities are available for them that make sense for where they're coming from. Rather than forcing them to go into a traditional mold, could we do a 10-week boot camp, right? Or what are the skills that are specifically needed to enter the field at some point and start giving you pathways or opportunities to maybe go back and do more education or go all in on, a technician role or an engineering role or things like that. So there is a lot of thinking right now going into regions where there's that high industry demand of what type of skills are needed to allow them to actually enter the field. And so groups are coming together to try to build out programming to meet that need and work with new communities. If we're talking about community colleges, regionality for the students is really important, right? They tend to have families there or be really integrated with their ecosystem. So if we train them there and then tell them they have to leave, it's not going to really help, right? So things like that are happening. There are a lot of programs that are focused on capacity building. So working with R2s or other MSIs, things like that, who want to create quantum programs and start engaging their students. There's a lot of programming going into that now. But again, it's trying to find the what can we do outside of the norm to meet the students where they're at so that they stay engaged and they'll actually want to work in the field. And that's challenging, right? Especially for institutions who don't have a lot of resources, a lot of support, things like that. A lot of onus is put on the individual professors, right? Or one or two people that are tasked with doing everything. So I hope I answered a little bit of your question. There's a lot of competition with traditional microelectronics and quantum, things of that nature, but I think anything that's helping reach the new communities, prepare people to enter the workforce in new and different ways, like through credentialing, through boot camps, things like that. People are really excited and interested in it, and I'm hoping within the next 2 to 3 years, we'll see some real programs develop out of that.
So what, generally, I guess maybe to all the panelists, is what a lot of the workforce development, it seems like, are in addition to your day-to-day work. So what are some, within the time constraints and maybe resource constraints, what are some realistic trackable milestones in workforce development that you can, you can
Resources are always an issue. I mean, just the job of a professor is like this really long list of things, and you can only ever do 30% of what you think you should get done. So my methodology is I pray every day, and what's supposed to get happen will happen. Comments on like how can we kind of really shift things, right? One of the things that I'm very passionate about as an educator is getting the conceptual foundations of quantum mechanics, making that accessible to everybody. And so that's why I do the YouTube channel. That's why I actually did a course with Wondrium that you can stream that has about 24, I think, lectures on quantum mechanics with no math. And through that platform, for example, I get comments from people who watch those lectures that, my favorite one is a student who went to my alma mater, Caltech, and said, look, I was a physics major at Caltech too. I took all these classes in quantum mechanics, and now that I watched your Wondrium course, now it makes sense. And I think this is a very common experience of a lot of students. They go through these really intense quantum classes where they have really intense mathematics and they can calculate things, but why did they do it and that sort of thing? Those conceptual foundations I find are actually lacking in the textbooks. So where do I get the conceptual foundations? Excuse me. Well, having taken the classes myself and thought very deeply about it, but I'm going to give you my go-to textbook for the concepts is actually the Feynman lectures. I love the Feynman lectures, and they're freely available online. There's a whole volume on quantum mechanics. And so a lot of what I do to pull this stuff and take it into, say, the middle school level or the general public level is actually, I study the Feynman lectures and how Feynman talked about it. What I love about Feynman, y'all, is that, so, not only is a Nobel Prize winning physicist, but he's a good communicator. He's always correct. I cannot say that about any other textbook writer. I always find an error. I haven't found one in the Feynman lectures, okay? So that's very nice to know that there's a place you can go and you can hang your hat on it and he's not gonna tell you any lies. So that's why I depend on him a lot in order to pull these concepts out and translate them in. Another trick that I use in that is I'm always looking connections back to your everyday life. So when I was talking to you earlier today in my talk about phase transitions, I took it back to a glass of ice water. I'm always looking for how can I take these esoteric quantum concepts and tie it back to something you already know, so you're on familiar territory, and I can pull you back to where I want you to be. So for example, you may not know this, but you actually are using quantum clocks every day. So anytime you pull out your phone, right, and you check the time, okay, it's what is that, 12:13. So we have how many minutes left?
Let's give ourselves a little close to 10 minutes.
Okay,
so
I just used a quantum clock, actually several quantum clocks. Why is that? I'm pulling the time signal off of the GPS satellites. The GPS satellites work by quantum clocks. And so that's pretty fun. Like, you actually just have ways that you use quantum in your life every day. So I'm always looking for those connections to bring it back to people. Another fun fact, GPS, right? So I have to send those signals over such large distances and gravitational differences that we use not just quantum mechanics to several places of the decimal. We use general relativity to several places of the decimal. We use special relativity to several places of the decimal. And not to make people panic, but those theories are incompatible with each other. Technically speaking, you're using, we don't actually know how they go together. We're just using them in different parts of the system. We use the general and special relativity for the long distance stuff, the quantum for the short distance stuff. We don't have a theory yet for how those go together. So if you really want to get at the foundations, come join us there at that interface.
Yeah, so I like the piece, and that's what I do too. Can you connect it to real life, right? You introduce tunneling, all you have to put up is your reading glasses and say, look, there's some tunneling there. It's an electromagnetic wave that goes through a dielectric. It's the same math, but you can describe it and you can relate. Electrical engineers know about bandpass filters. That is what a band structure is when you inject into a superlattice. It's the same stuff. You can connect it to things they've seen before if you can. So that's a key element. I go back to resources. There is, for example, in semiconductors, an effort called SCALE. And it's a very large program, connects some 20 universities that create content for semiconductors, specifically for the American military-oriented or national lab-oriented customer base or student base. So they put their money where their mouth is, and they chose NanoHub to put their content in an aggregated fashion. But I want to raise another issue. If you look at minority serving institutions, they have 98% of their constituents are US nationals. They come from relatively local areas and they serve their communities. So if we need to reach American students and bring them up and offer them new opportunities, that's the place to go. So everybody talks about minority MSIs. How many technical MSIs are in the nation? Do you have any idea? We always talk about it, right? But you go to any audience, they have no clue. They talk about it. There's about 350 technical MSIs in the United States, right? So how do you get to 350? You actually take real effort. You create content, not for them, but with them. And then you market that material to other universities that are like that. You scrape the web. You actually set aside secretary time to scrape a web, go from website to website, because it's very fragmented. You peel out faculty and member names and emails. You put them into a Salesforce instance and start marketing content to them in a systematic way. So who of you wants to do this kind of stuff? Which faculty member wants to do this kind of stuff? It doesn't just grow naturally. That I can guarantee you. So you have to put real effort into that. A real thing. Real effort. And I can guarantee you, just like Erica or any of the faculty members, I can do extra efforts between 2 and 3 a.m. in the morning. That's about it, right? So we need to find people that are dedicated, that are similar to us, but they're dedicated to this kind of stuff.
To that end, I guess most of the audience are graduate students and postdoc, and it seems like to become more like the panelists on here, you also have to spend the time not just knowing the information, knowing the theory and everything, be good at your courses and your specialty, but also have a way of translating it and communicating it. How do you go about becoming a better science communicator generally? And do you think there are methodologies for kind of everyone to get on board to take part in this effort, so it's more widespread and everyone can go ahead and, I guess, preach the gospel?
Well, you know what I do. You were in my class.
Well, I know, but beyond one professional development class, do you think there should be more?
There should be more, and we should be open and tell people when their talks are shit, and actually tell them it's not good enough to just throw information like an array of 3x2 data graphs that nobody can read from the back of the room and then talk for 5 minutes to the same slide. I mean, it's a terrible way of giving a talk. You either want to convey information or you want to show how good you are. Those are the two different things.
I'm chuckling thinking of all the seminars I've watched. And anyway, you and I should sit in the back and trade notes, take notes on how people give talks. Anyway, so science communication. So as an educator, a professor who teaches a lot here at the university, and right now I'm getting to teach like my dream course, which I got the name changed and everything. It's now called Introduction to Quantum Science, and we teach it at the sophomore level. So it's the most introductory course at Purdue that has the word quantum in the title. And we have a section for physics majors, and we have a section for engineers. And so Introduction to Quantum Science, and like you were saying, and there's a big difference between content delivery and actual communication. So I need a piece of paper. Send me a piece of paper. All right. Ooh, wow, that's almost, that's great, perfect. Okay, so I'm gonna demonstrate the difference between like just a good communication and poor communication. Here, catch. That was bad. All right, try again. Right? I mean, that's bad communication, right? The good communication is I actually want you to receive it. You ready? All right. Perfect. That's the difference between good communication and bad communication. One worked, and I had to actually connect with the recipient, right? And so in a classroom setting, for example, I make these videos for YouTube, and it's actually challenging for me because I have to practice in front of real people first so that I know what catches and what lands. And so when I'm in a classroom, you were talking about the situation of, you've probably experienced this with one of your professors, slide full of equations or whatever, and you see the person's back and they're kind of mumbling for 5 minutes. It was sort of like the first thing I did, where I just sort of threw it past you and it didn't really connect. So in a classroom setting, and actually, Purdue's pretty big on this with our Center for Instructional Excellence. We train professors to be interactive, right? And so to really, rather than just aiming a stream of information past you, you've got to be taking the pulse of your audience or your students all the time. So in fact, if you're ever in one of my lectures, you know that I'm very interactive and that I'm talking, it's a conversation back and forth. Yeah, I have an agenda for us that focuses us, but I don't want to move from one topic to the next unless I'm sure you actually caught the message, and then we can move on. And that absolutely requires a conversation. So I'm always having a back and forth discussion with my students. It might take me a little bit longer to get through some of the content, but it's so much more fun to be talking with the students, because to really communicate well, I have to know how you're thinking, right? I have to get inside your head and know, and I don't know unless we have a conversation. Yeah.
So when I teach solid state semiconductor devices at 606, it's the core course for any grad student that's in semiconductor, nano, whatever. I spent all summer of 2020 recording the lectures, highly animating, making it one to many, but being didactic and animating things, and not a wall of equations, but this is important, let's talk about it, right? You were in the class. and then I tell the students, okay, you don't want to hear me give the same lecture over and over again. It's boring to me. And I worked really hard. I did many retakes of videos and all that. Instead, then I do a recitation. I let the students, I mean, we walk through the semester, I let the students ask any questions. And as a faculty member, that's actually kind of scary because they can ask about anything. I mean, anything, right? And you're not necessarily prepared, have something canned in the back of your head. You have to be spontaneous and improvise. And sometimes you have to say, I don't know, I have to look it up. I don't remember, or I've never heard this aspect, right? So it keeps you humble as well. So showing that humbleness is actually a fine way of sharing that. That's my take.
So to go with some of the earlier question too about for the graduate students looking at how to become better, more effective communicators, I think part of it also comes from wanting to do that. It doesn't just happen completely naturally. You need to focus on it and put in effort. And so as you're going around to conferences, you should have in the back of your head this idea of like, oh, you know, I just sat through like a really good presentation. What about it was making it so effective? And you can try and take those strategies and start applying them in your own work. And likewise, if you see a really, really bad presentation, you can try and avoid those kinds of things. And there are plenty of books and lecture series and things out there to try to communicate some of this stuff to you. And you can go and engage with some of those resources, certainly. But at the end of the day, it takes the time, it takes the effort, and it takes the practice to build those things. And you have to keep focusing on it and not just, you know, wishing that one day you'll wake up and be an amazing communicator.
So I learned one recipe from Supriya Datta, who I consider the best teacher I've ever met. And he was my advisor. And he basically told me, structure your talk into 3 components. And whatever time, 60-second elevator pitch, 45-minute lecture, 12-minute APS seminar, doesn't matter. Divide in thirds. The first third, you tell the audience why they should be interested. What are the problems? Why is this relevant to them? You engage them. You make them understand that they should be almost working on that. They should feel like this is really important and I want to listen. In the next third, you show them your beautiful solutions. No equations. You teach the audience. It should be simple. It should be Feynman simple. If you can't explain it easily, you don't understand it well enough. That's Einstein. So the second third, you teach. No jargon. And then the audience should feel ashamed for not already working on this. Because it's so cool, right? They should be working on it and they can learn something relatively easily. And then for my own, I subdivided the last 2/3 and you blow them out of the water in the 1/6. And you show them why you're the expert in the room and you really know your stuff. And you do all the stuff that all of you do on slide number 2 and 3 forward. Show them equations, show them whatever you want to do. But it's short and you can capture them back in the last 6 where you can tell them what you're going to do for them in the future and how you're going to propose something or how you're going to get money or what you're going to do next with your PhD, right? What the future holds and how you share that with the audience. So 1/3 motivation, 1/3 teaching, 1/6 expertise, 1/6 future. And you can do that with anything and you keep the audience. So if you're going for an interview at Intel or wherever you might get a job, if managers start opening their iPhone and read their email on slide number 2, you will never get them back. Never. There will be one person in the audience out of 20 that will listen to your interview talk that knows the technical depth. You want to talk to the 1 in 20 or you want to talk to 20? That's your choice. Do you want to talk to one person in the audience or the whole audience? You have to always ask yourself, does my audience understand what I'm going to say? If they don't, you're wasting your time and you're wasting their time.
Well, I remember that. So that's great. I just, before we end, I just curious how, I think this has shifted more on the discussion of science communication since it's such a big component of workforce development. What proportions of current grad students and postdocs leave their posts, kind of moving on to the next thing, do you reckon what's the proportion you think people are a good communicator, and what portion do you think are just extremely poor communicators, and what do you think the frequency people should be practicing and presenting all the time?
So what I did when I had a group of 35, every week anybody had to be able to present for 15 minutes, and I would call. We had a Wheel of Fortune or Unfortune. Your name was on there. You give a talk of what you've done in the last week, 2, 3 weeks. You had to be prepared. If you work in industry, you don't know if your boss walks in and says, by the way, you got to talk to the CEO or the division manager this afternoon at 3. DIC nods. It's normal. The stuff just shows up in your work environment. You have to be prepared at any time to give a talk. And you might say, that's bullshit. No. On Tuesday, I gave a briefing to SRC. The guy loved the thing, and he said, I'm going to have you present on Friday to an executive committee that is building a big CHIPS Act proposal. So I just came back in the morning, and I had to be ready to present for 45 minutes on something that is different than what I showed the day before. Right? Mm-hmm. It is real. You don't know when you're going to be called on to talk. So you have to be ready all the time with small modifications where you can adjust for the audience. So I spent 3 hours last night updating that talk for the audience that I was going to talk to. So I took whatever I had on Tuesday, which was pretty well developed, but still I mucked around 2.5 hours, almost 3. It takes time.
Any other thoughts from the panelists on?
So I can't answer your last question, a little outside my area of expertise, but just doubling down on the connection and storytelling piece, right? That's most important. I'll tend to talk the most to folks who know nothing about quantum, right? And that probably came through. But it's making it relevant. It's making it so that they do get excited about it, right? And you guys have all said it very well. But that is such an important piece, especially if you're talking to people who aren't familiar with what you're doing. So yeah, that was the only other thought that came up.
One more thing. You guys are all great giving people solutions to problems they don't have. So why would they listen? That's the whole point, right? We come on slide number 1, there's Moore's Law. It's awesome. And slide 1.5, you say, I'm going to save Moore's Law. And then you show umph degree of detail that has nothing to do with Moore's Law. And you conclude with something that has nothing to do with your motivation. Well, makes no sense. So you provide solutions to problems that people don't have. So if you have solutions, you have to make them relevant to the audience.
How many of the students are hungry?
They ate already.
Yeah.
Just saying.
All right,
Lunch is next,
let's
right?
open up for any more last-minute questions from the audience, and then we'll finish up.
Hi, thank you for the insight. Maybe it's a question more to Jake. So a lot of the quantum technology, including quantum computing and quantum sensing, they're still at a very early stage of the development. So you have shown that you believe through your research, you think the industry is gonna take off. What make you confident from the research that make you confident that this is gonna happen?
Yeah, so I'm an optimist, so probably not the best person to ask about the real technical foundations, right? If we're talking about sensing, it's already here in a lot of ways, right? With atomic clocks, we're trying to figure out how to improve them, make them smaller, things like that. But application is already shown. If we're talking about magnetometry or gravimetry, things like that, sensing applications are demonstrated. They're just lab scale, right? And it's trying to get them miniaturized and better than classical options. But within sensing, it's already kind of here. Within the next few years, we're going to see it going. And a great way to kind of gauge on if it's going to be successful or not is what industry is doing, right? They have to make money, they have to prove it. And there's enough going on there outside of kind of the scientific community showing that there's broad belief amongst everyone that something's going to happen. Computing, right? It's the potential piece. Whoever gets there first is going to have a huge advantage, across the different domains that people think it's going to really affect, right? So we don't have that killer app yet, right? We haven't proven advantage, but people can see the potential if we are able to solve those 7 or 8 really, really hard problems to actually get there. So in the technical grounding piece of things, again, not quite my area of expertise there, but the foundational science that's being done, the amount of progress that's been made, and the potential impact it can have is what I see really driving the field.
All right, thank you. So, one more question. All right, one last question.
Just a quick follow-up, but I think, was it 80% of the skills in your jobs are non-quantum for those quantum industry things? So I would also say that you can hope to maybe, have the quantum industry there, but it shouldn't necessarily need to be there. As you're going through all of your program and all of these graduate degrees that you're getting, you should be building so many additional skills that you're still very marketable to plenty other industries. And so I go with the optimistic approach of, yes, I'm training my students in quantum, but I'm also ensuring that they have skills in a broad spectrum of other technologies and still understand classical engineering and things like that, so that they do have that, maybe I wouldn't even call it a backup necessarily, but it's just something that should be there with the way you're going through your program.
That's true for almost any industry job anyways. The 20% are the specialty that they almost assume you can learn them if you have the other 80%. When you go to industry today, almost nobody truly knows chip design. They might have taken a course. They grow that capability on the job. They hire people to solve hard problems. And by the way, it's extremely unlikely that anybody is going to hire you again to re-implement your own PhD thesis. It's been done. Nobody will do that again. And most likely it's irrelevant anyways. So you will do other stuff.
All right, one last question.
Hi. So we've talked a lot about how to talk to middle schooler, to high schooler, to undergrad, but I want to look at the other end of the spectrum, which is to talk to politicians to make sure that the funding doesn't dry up in the next 5 years. So I've been wondering, I don't see an incentive on how we can actually get them to allocate more funding, because it's not like this is going to solve the bankruptcy of the Social Security, or it's not like there's a Sputnik moment that the foreign powers are overtaking the lead for the US on quantum information. So what kind of pitch do we give people in Washington?
So when we had Secretary of Commerce here and Blinken, Secretary of State, I was being told, you have 2 minutes to explain nanomodeling. What do you do? So I had this, I don't have it with me, like a piece of paper. I said, look, there's a transistor. There's a red, a white, and a blue stripe. Source, drain, there's a gate, water flows through, you can squeeze it. Electrons are like water. I fold this thing in half, same picture. This is what happened 18 months later. Transistors got half the size, double the speed. Fold it again, same picture, blue, white, red. The guy got it. She got it. They understood something about Moore's law that they never understood before, and they realized how important that was for technology. And at the end, you deal with atoms. That's the stuff I model. So those people are then going out. She's leading the whole CHIPS Act out of Department of Commerce, right? It's $50 billion, right? And you have to be able to talk to them. I don't know that they convince other people to put in more than $50 billion. That's a different story. But you really have to, again, right? Who is the audience? What do they know? And can you let them walk away happily that they learned something? Don't talk to them about problems they don't have.
Yeah, so exactly that, right? So don't talk to them about problems they don't have. Rather, ask them about what their problems are and is there some sort of solution that quantum could offer that would be helpful for it, right? And quantum applications could affect kind of verticals across the entire board. So depending on who you're talking to, you make sure that you connect with what's relevant to them, how it might be able to help solve their problem and really why they should care, right? So if we're talking to big bankers, right? Hey, quantum might be able to help you do fraud detection in very new ways. And there are places like HSBC, a big bank, that have already proven with some current applications that they can improve fraud detection. They really care about that. Okay, let's invest a little bit more, right? Or if we're talking about GPS, what happens if it goes away? Well, hey, there's a quantum application. We might be able to do GPS denied navigation. So it's connecting back to the things they care about, right? And educating them about what quantum might be able to enable. I also want to say, without getting too hypey, that's something that's always a worry when we're talking to industry folks who might, promise the world. But if you can go through and have that viable story about here's what you care about and here's why quantum matters, that's the best way to tell it, especially if you can get the storytelling piece kind of built in, which we've heard a lot about already today from the other panelists.
Never leave home without it.
It's a planar transistor. Source, drain, gate, electrons flow one way, very thin, but very big. 18 months later, in '85, this device looked like this. Same, very flat, rectangular. 18 months later, it looked like that. If you're old enough, you know what an 8086 is, a 186, a 386, a Pentium, right? This is what happened for 40 years. Got smaller, got smaller. And this stuff is so small now, it's literally atoms you can count. That's the story. And why is it relevant? Because you have 8 billion transistors of that nature in your iPhone. I left mine in the car. 8 billion, that is larger than the number of people on this world working together without having a war and actually doing something consistent. It's a pretty large number and pretty amazing.
All right, thank you all for your questions. Let's thank the speakers and panelists once more. We're just gonna have Professor Bodhiseva close us out for the school.
Thank you very much. And thank you very much, panelists. And I think we should just thank one more time all the speakers, all the students, all the participants for making it a great success. But before we do that, I would like to give thousands, millions, and billions thanks to people who really did it all and who put this school together, from logistics and inviting people to the very, very tiny details. So I would like to thank David Stewart, our managing director. David. Tracy, thank you so much for all your help. Do we have Robert? Robert, yeah, on the back. Thank you so much. We have Thomas. Thank you for your help, especially with the last day with Elmore Center and machine learning. And Morris. Morris and everyone, all our moderators and session chairs, students, postdocs, everyone. I really, really hope that you had a chance to learn, to network, to build connections, to meet new friends, and most importantly, that you got inspired to learn more. And as we just discussed, reach out, ask questions. All of us are here to educate and to help you learn, but we have to have a better connection to understand each other and to make it more efficient. And I hope to see all of you next year. Thank you very much.